time for us to do a lot of practice with lines and planes. Well, really practice, but you'll see there's so many variations that we can do. So we might be here for a while. So go get your popcorn and, of course, get your notes and be ready to do some work. It's important that you do as much work as you can. The more problems you do, the more you start to develop your geometrical intuition, and then you're starting to understand how things fit together. If you're following along with the video, consider making frequent use of the pause button. See a problem you like? Pause it and try to say, how would I approach it? And start working the problem. Then you can unpause. Now it's going to happen a couple of times that there are multiple ways to do a problem. So, but at least we can compare our answers. In a few cases, I'll try to show you multiple different solutions. I will, as much as possible, try to go at a little bit faster pace just because there's so many fun things. But I fear I may not be able to stop myself when I see so many beautiful problems. There's going to be a lot of good ones here. So let's enjoy the ride and begin. So, our first problem. Find the line which passes through the point 2, 1, 4, is parallel to the plane 4x plus 5z equals 19 plus 3y, and intersects the z-axis. So we actually have a couple of things going on here. So what can we think about? Well, we have a plane. So okay, let's draw ourselves a plane. So here's our plane. And again, we're not worrying about being accurate. We're worrying about getting an understanding. And what do we want? Well, it has to go through a particular point. So here's the point 2, 1, 4. We have to be parallel to the plane. Now we have to decide what that means, because it's not necessarily automatic that we parallel. Because oftentimes when we think of a lines being parallel lines mean same direction, or at the very least, if we look at their direction vectors, they're parallel to each other. But how do we think of a line being parallel to a plane? Well, sort of the intuition is in parallel lines, if we think in 2 dimensions, they don't intersect. So we say, okay, a line and a plane will be parallel if they don't intersect. Now, suppose I have a plane and I have a point. How many lines passing through that point are parallel? Well, the thing is, if I have this plane, I can think of my line up here. I can sort of have this rotation going on, and no matter which direction I point in, lo and behold, I'm still not going to hit the plane. So there's infinitely many lines that go through that one particular point and are parallel to the plane. And among all of them, what do we want? Well, we have to add one more condition, because we have to have a unique answer, otherwise this is a crazy problem. And the answer is, well, there's an axis somewhere over there. You can't see it, it's off camera. Z-axis. So it's like we're turning our line, so just so it's going to go and hit the z-axis. That's our goal. Okay. So, how to begin? Well, all right. So we have our three-dimensional coordinate system. Here we have our plane, and now we have to think about what to do. Well, probably there's a couple of different ways to do this one. Let's just start with the following. Let's suppose we had our point on the z-axis. Now, if we're on the z-axis, we know what our point has to look like. It has to look like something in the form 0, 0, and I'll say a, where a is some number to be determined. If I knew a, I'd be done. All right, well, let's think about what's true. Well, let's suppose for the sake of continuing in the problem, we'll treat a like it's something we did know, and we'll see what conclusions we can make. Now, one thing we could do is we could draw the vector that connects our 2 points together. So here's this vector. So it's the vector that goes 2, 1, 4 to 0, 0, a. So that vector does what? Well, goes down by 2, goes down by 1, then down by 4 plus a. So this would be the vector that is the direction of the line. So here we have our direction of our line. Well, if we knew a. Okay. And now we start thinking about that. we say, hold on a second. If it's the direction of our line, we can think about the fact that it's parallel. So if I have my plane down here, have my line, the fact that it's parallel says if I just shifted the line down, it would still run exactly in the plane. So if I'm parallel up here, that means if I move down, I'm in the plane. What does that mean about our direction vector? Well, that says that the direction of the line is a direction of the plane. That's a key. So we say, aha, this is going to be a direction which is in the plane. Of course, we always think of when we say it's in the plane, we mean that there is a vector that is in the plane that has that as its component form. All right, now, believe it or not, we've had a great aha. Well, why? Because once we know we have a vector in the plane, we know something about planes. There's the normal vector. The normal vector is perpendicular. So let's look at our plane. Now, it's written a little bit strange here. If we rewrite it, that can become 4x minus 3y plus 5z equals 19. And the normal is the coefficients, 4, -3, 5. Now, we did a little bit of rewriting first just to make sure that when we grabbed the coefficients, we didn't accidentally put in the wrong sign. See, if we had said, 4, 3, 5, wrong, we would be in trouble. All right, now, here we go. This is a normal vector. And we say to ourselves, aha, I have two vectors which have to be perpendicular to each other. The normal vector is always perpendicular to everything in the plane. If I know two vectors are perpendicular to each other, I know something about their dot product. Dot product has to be 0. So we can say the following. 0 has to be equal to minus 2, minus 1, minus 4 plus a dot 4, -3, 5. Well, take the dot. Minus 1 times 4, -4. Minus 1 times minus 3, plus 3. Minus 4 times 5, minus 20. And then plus 5a. All right. Well, that's something. Good. So now we have our pieces. Well, minus 4 plus 3 minus 20 is minus 21. Okay, move it across, and we can say that tells us 5a is equal to 21. All right, well, sure, it has to be something. So, okay, so that's what a is. That's what a is. All right, now what? Oh, wait a second. I made a copy mistake. Can you see it? I put minus 1 here. Dope. Can't believe it. Minus 2. I was worried here. Not that it's not a nice number, but it's just not as nice. All right. See, minus 2 times 4 is minus 8. That's the good thing about working on beautiful problems. When you're working on beautiful problems, you should get beautiful answers. All right. That's more reasonable. See, minus 8 plus 3 is minus 5. Minus 20 is minus 25. So that really says 5a is 25, or a is 5. So that's perfect. What do we know? Now, since we know a, we can come up here and update. There's 5, but also we can come up here and say, look, minus 4 plus 5 makes it 1. So now we have a point, 0, 0, 5, and a direction, minus 2, minus 1, plus 1. Point plus direction, we're good to go. So let's see. Let's write down our answer. We have x equals, y equals, z equals, and we're going to have our point. I'll use 0, 0, 5. I could use 2, 1, 4. It doesn't matter. I like 0, 0, 5 because it has zeros in it. More zeros usually tend to mean easier computations at some point. Then our direction vector, all right, plus minus 2t plus minus 1 times t, and then plus 1 times t. So 2 minus 1, 1. Or we could just simply say x equals minus 2t, y equals minus t, and z equals 5 plus t. And that's our line. It passes through the point 2, 1, 4, and also it hits the z-axis, and it never hits the plane. It checks all the boxes, and we're done. Now, let's try a different way. Okay, so what's our other idea? Well, our other idea, we'll simply say, look, I'm after that point. I'm still after where do I hit the z-axis. And the idea is I said, look, I had this line before, this plane down here. And I said, think about it. This line is down in the plane. Okay. And then we said, all right, that gives us a direction vector in the plane. And now we can find something about the normal. Okay. Let's do kind of the opposite. Instead of moving the line down, let's move the plane up. So the idea, sort of intuitive what's happening here, is we're going to put this plane and then we're just going to move it directly up. So what do we mean? Well, we're going to have a plane with the same normal vector, but it's going now to contain the point 2, 1, 4. So here we go. So we're going to form a new plane. And the new plane is going to be parallel to the old plane. So it means that the normal is going to be the same normal. The way you make two planes parallel is you make the normal vectors parallel. See, that's the nice thing about talking about direction in terms of the normal vectors, is you just say, hey, check what's happening with the normals. So it's going to have the same normal, 4 minus 3, 5. And now we're going to say, but we're going to make sure it has our new point, 2, 1, 4. So what have we done? Well, now we've said, hey, there's this point up here, and now we've moved and said, here's the plane. Our line has to be in the new plane. Well, what is our new plane? It's not so hard to write down. It's 4x minus 3y plus 5z, right? Because the 4, negative 3, and the 5 are the coefficients, equals something. Well, all right, do a little bit of scratch work underneath here. Plug in 2, 1, 4. So we're going to get 4 times 2, 8, then minus 3, 3 times 1, plus 5 times 4 is 20, equals 25. Okay, that's our new plane. Now, our line has to be in our new plane. And so, wherever the plane hits the z-axis, that's the only place that the line could hit the z-axis. So now we say, okay, where does the plane hit the z-axis? So the plane hits the z-axis. So we have, now what's true about points on the z-axis? That's kind of the key idea. That means that x and y equals 0. So you plug in x equals y equals 0, and you get 5z equals 25, or z equals 5, giving us the point 0, 0, 5. Exactly what we had. And now the problem goes as before. See what's happened? We had our original point, 2, 1, 4, and now we found where we hit the z-axis, and now we've got 2 points, and off we go. All right, so we could say, look, take a dot product set equal to 0, or think about moving a plane up and down. Either way, we end up with the same answer, which is good. It should be consistent. More than one way to solve a problem. Well, good. Now, let's go on and do a lot more problems. Okay, we're going to get great at this stuff. Our next problem. Find the line in parametric form containing the point 0, 1, 2, and which perpendicularly intersects the line x equals 1 plus t, y equals 1 minus t, and z equals 2t. All right, so what's happening here? Well, we have a line, So here's our line. And we'll mark a typical point. So a typical point looks like 1 plus t, comma, 1 minus t, comma, 2t. As you vary t, it's going to move along the line. Lots and lots of points. Now, in addition, there's another point sitting somewhere. Let's say it's here. So here's our other point. 0, 1, 2. Now, we have a point, we have a line. Our goal is we want to construct a new line. And that new line does the following. It intersects our original line perpendicularly. Well, it means that we're going to find somehow a line such that it hits the arrowed line, but it does so at a nice right angle. All right. Well, how can we do this problem? We're going to have a little bit of shades of the past problem. So if you remember the problem we just finished, this sounds very different, but after we get into it, it's like, hey, we're doing some of the same ideas. And there's going to be a common theme. We don't have that many tools. It's not that you have a large set of tools. We have a small set of tools, and it's just about learning to use them well. And you'll see that over and over. It's like, oh, let's use these similar ideas, just change the setting. So we'll do two different approaches again. Now, what's our first approach? Well, there's sort of a philosophy. And here's the philosophy. If I'm asked to find a line, what I can do is I can find all the lines. So you're like, well, that sounds like a lot. Well, yeah. But then after I found all the lines, I go through and I pick out just the right one. So in other words, instead of trying to focus on just finding a single line, just say, let's be super generic, find everything that it could possibly be, and then examine the ones that we end up making. Okay, so we'll call this one the find all the lines approach. So how do we do that? Well, what we do is we ask ourselves, what's true? Well, in particular, we're going to say, let's think about the direction of the line. Now, we'll drop a constraint. Between the two, we can draw perpendicular and say, look, suppose I didn't have to worry about perpendicular. Let's just say I'm going to find all the lines which intersect the other line. Now all of a sudden it's super easy to talk about it. Because what we do is we just say, well, I just connect. And I ask, what's true about that line? Well, in particular, what's the direction vector? I can start from my point 0, 1, 2, and I can head over to my generic point. And I say, all right, I go from 0, and I go to 1 plus t. So that's a change by 1 plus t. I can go to 1. If I go to 1 minus t, I went down by t. And from 2 to get to 2t, I went minus 2 plus 2t. So that's the direction vector of a line which goes through our original point and intersects our other line somewhere. Not worrying about perpendicular. And of course you say, look, you've not made one direction vector, you've made this massive family of direction vectors. And we have. We've truly made a large collection of direction vectors. There's going to be one of them for every single place we could intersect. So now there's this huge collection. But now we say, good. Our direction vector looks like the following. So direction is going to be 1 plus t minus t and minus 2 plus 2t. And now let's go back and put in the perpendicular. We know it has to be perpendicular to our original line. So we need it to be perpendicular to the direction of our original line. Do we know what that is? Well, let's read it off. How do we read off the direction of the original line? Look at the coefficients here. So the coefficient for t, for x, is 1. The coefficient for y is minus 1. And the coefficient for z is 2. So there we go. 1, minus 1, 2. That has to be the direction. Sorry, that's the direction of our original line. that has to be perpendicular to the direction of our new line. And now we say, wait, if I have two things which are perpendicular, what must be true? The dot product has to be 0. Okay, so we're going to take their dot product, set it equal to 0, and good stuff should happen. Well, because we live a good, clean geometry life. So we have that 0 should 1 times 1 plus t, 1 plus t, minus 1 times minus t, t, 2 times minus 2 plus 2t, well, that'll be minus 4 plus 4t. Yes? Yeah, I think so. That sounds right to me. And, well, this is the same as 1 minus 4 is negative 3. T plus 4t is 6t. Or we could say t equals 1/2. Now, what does this tell us? It tells us that if we plug in t equals 1/2 into our line, that will produce this point. But in essence, we really don't need that. What do we really need? What we really need is the direction of our new line. So we're going to take this quantity and we're going to put it into our direction vector, because that's going to give us the exact right direction vector. So we get 1 plus 1/2, which is 3/2, minus 1/2, okay, and then minus 2 plus 2 times 1/2, minus 2 plus 1. All right, minus 1. All right, and there we go. So this is our direction. We already have our point. It was given to us. Point plus direction makes a line. So we can write down our answer. So our answer will be the following. We have x, y, z will be equal to, we plug in our point, 0, 1, 2, 0, 1, 2, and then we use our direction. And 3/2 t minus 1/2 t and minus 1 times t. Or, if you like, you can say x should be 3/2 times t, y should equal 1 minus 1/2 times t, and z should equal 2 minus t. And that satisfies everything. And we're done. By the way, if you don't like fractions, you can actually do something at the stage here where you found the direction vector and you say, look, the direction vector, I can scale it by any amount. So if you just scale, you could say, look, 3 minus 1 minus 2. That's my direction. Perfectly fine. Perfectly fine, because we only need the directional aspect of the direction vector. So you can scale it to be anything you want if you want to avoid fractions. If you don't want to, perfectly fine as well. All right, now, do it our second way. Round 2. How are we going to do round 2? Well, let's sort of go back to an important idea. And here's the important idea, that if you think about 2 dimensions, you have this sort of nice interplay, which is a plane is 2-dimensional and a line is 1-dimensional, of course, and that gets us up to dimension 3. Now, it's kind of a weird sort of idea here. What am I trying to say? Well, what I'm trying to say is if you have a line, well, you can think about it as there is some sort of a plane associated with it that's perpendicular. And if you have a plane, there's a line associated which is perpendicular. Now, of course, it's not unique. So if I start with a line, the plane I can shift up and down. So you have to say, okay, shift it to where? If I have a plane, the line I can move around. But again, I just have to decide where. Now, I'm given a line, the original line. So what we can do is say, let's make a plane that's perpendicular to that line. So I have my original line, and I'm going to make a plane perpendicular to it. So I have to decide, where do I set my plane? Well, I'll set it right to the place so that it contains our point, 0, 1, 2. So let's talk about our pieces here. We know the direction of our line, original line, is going to be 1, minus 1, 2, and we're going to make this the normal to our new plane. Now what? Well, that means that our plane looks like x minus y plus 2z. And we're going to set that equal to what? Well, plug in 0, 1, 2. So we got to do a little bit of computation here. So x is 0, y is 1, and z is 2. So 0 minus 1 plus 4, which gets us to 3. Okay, so there we go. There's our new plane. How do we use our new plane? Well, now, what do we have? We have a plane, we have a vector. Sorry, we have a plane and we have a line. Where do they intersect? So we've sort of, what's the picture? There's this plane here now. It's perpendicular to this line and contains that point. Find the intersection. So the way we do that is, where's a color I can use that will help us follow the logic here. I'm going to take a point on the line and I'm going to plug it in for x, y, and z. So doing that gets us what? 1 plus t minus 1 minus t plus 2 times 2t equals 3. Now, if you clean this up, what will you end up getting? Well, what you'll end up getting here is you'll have t plus 4t, which is 6t. And then you'll have the ones and the ones cancel equals 3, or t equals a half. And you might say, hey, we've seen t equals a half before. It's this t equals a half that we saw. So at this stage, we've now figured out, when you plug in t equals a half, that gives you this point. And once you have that point, you make the vector, and life is good. And so that's another way to go about it. So they both work. They're not completely unrelated, but they may not feel the same when you first think about it. Which way is the right way? They're both right. And you do it the way you understand, and the way that you're least likely to make a mistake. That's important. We don't want to make mistakes. We like to get the right answers. All right, good. All right, well, let's go on to another problem. Find the line that intersects the line 1 plus t, 2 minus 3t, comma 2t perpendicularly and lies in the plane x plus y minus 3z equals minus 1. Now, this is kind of an interesting thing. So we're looking for a line. So that's good. We know what we're after. It's always good to identify what is it we're looking for? A line. And so what do we need? Well, we need two pieces of information. If we're looking for a line, we need to talk about the point, and we need to talk about the direction. And those two things together make up a line. And once we have them, we're done. It's easy. Just write down the answer. So we got to think about, how do we get those things? How do we get the point? How do we get the direction? So draw ourselves a picture. We have a plane. So here's a plane, and it's doing something. So our original plane, x plus y minus 3z equals minus 1. And then we have a line. Now, what's happening? Well, this line is coming into the plane. We want to be careful in our picture that we don't sort of force anything in it. So I'm going to draw it to really emphasize that we don't really know what's happening. So in particular, you might be tempted to draw the picture where it's like, oh, here's my line coming down. But we're not told that our line is perpendicular to the plane. So we're going to draw it, since we haven't been explicitly told anything, we don't want to force ourselves to think that there's this extra constraint. So it's coming in at sort of a skewed angle here. So it probably isn't coming like that. It's coming in more like that. Now, if you think about what's happening, wherever it hits the plane, there's going to be infinitely many lines that pass through that point that stay in the plane. So there's all these lines here. So there's all these lines that are coming through. They're all in the plane. And now the question becomes, great, which line do we want? Well, among all the lines that are there, there's going to be some line such that it's going to be exactly perpendicular to the line that we started with. So our goal is find that line. So we have to think point and direction. So let's start with the point. Well, our point has to be what? It has to be in the plane and on the original line. So to find the point, we think to ourselves, okay, let's look at the intersection of the line and plane. And the way you find the intersection of a line and a plane is you say, all right, we know our x, y, and z in terms of t, so we take this information and plug it into the relationship. So x is 1 plus t, y is 2 minus 3t, and then z is 2t. So again, what have we done? We've simply taken our old equation, which said x plus y minus 3z equals minus 1, but replace what x, y, and z are in terms of functions of t. Now we start cleaning it up. We'll have a t minus 3t minus 6t. Well, that's a lot of t there. So t minus 3t minus 6t would lead us to minus 8 times t. Then here you get a 1 and a 2, that makes 3. Move it across, equals minus 4. Or, you can divide, t should equal a half. Okay, so now we say, look, at t equals a half, that's the spot where the line hits the plane. Well, now plug in t equals a half and read off the point. 1 plus a half, 3 halves. 2 minus 3 times a half, so that's 2 minus 3 halves, or 2 minus 1.5, which is a half. And then 2 times a half, well, 1. So 3 halves, 1 half, 1. Good, there we go. All right, well, now what? From here, we say, got to turn to direction. That's the only thing we don't know right now. So we think about direction. Now, if we don't know our direction, one of the things we can start asking ourselves is, what can we say? Well, we know it has to be perpendicular to our original line. So we say, okay, our original line, we can read off the direction vector there. So we know it has to be perpendicular to 1, negative 3, and 2. So that's coming off 1, negative 3, 2. But remember, we also know it has to be inside of the plane. So if I have a line that's in the plane, so here's my line, here's my plane, then the direction of that line, that vector, has to be a vector which is contained in the plane. Aha, and any vector which can be contained in the plane is perpendicular to the normal vector. So it also needs to be perpendicular to 1, 1, negative 3. So the geometry tells us, hey, whatever our direction vector is, it's got to be perpendicular to 2 things. And now we look at this and say, whoa, perpendicular to 2 things, we're going to use cross product, because that's how you take a vector that has to be perpendicular to 2 things and figure out what it should be. So here we go. We're going to have I, j, k, 1, minus 3, 2, 1, 1, minus 3. So what does that become? I times minus 3 times minus 3, 9i. J times 2 times 1, 2j. K times 1 is k. 1 times minus 3 times k, minus 3k, but don't forget we need to subtract, so plus 3k. 1 times 2 times I, 2i, but don't forget you have to subtract, minus 2i. And minus 3 times 1 times j, minus 3j, but you're subtracting, so it becomes plus 3j. So it looks like it should be 7, 5, 4. Well, it looks like it. Let's check it. So dot product. 7 plus 5 is 12, minus 12 is 0. Good. 7 minus 15 plus 8 is 0. Perfect. Perfect. So now we have our direction. 7, 5, 4. With a point and a direction, life is good. It's so good, we just write down the answer. So let's write down the answer. We have that x, y, and z is, well, for our point, we put that in. So we have 3 halves, 1 half, 1. And then, of course, the next thing is we have to put in the direction. Well, that's going to be the coefficients of the t's. So we have 7, 5, and 4. So that's a weird looking 7. 7. There we go. That's a more normal looking 7. So 7 times t, 5 times t, 4 times t. And that's our answer. Now, oftentimes I do write my answers in parametric form. I have a strong preference for that. If you prefer vector form, that's great. So in vector form, what would it look like? It would be 3 halves, 1 half, 1, plus t times 7, 5, 4. And that's a perfectly fine way to write your answer as well. Do it whichever way you need to. Of course, if you're taking an exam, doing some sort of a homework, follow the instructions. It's great advice. Follow the instructions because you're more likely to get points. And that's what we want. We want points. Well, we really want to understand. Points are just an added bonus. So let's do another problem. Find the distance from the point P, 1, 1, 0. Now, if you're not familiar with what this notation means, when you see a number followed immediately, that says there is this point we're calling P, and that point is 1, 1, 0. So it's just saying label a point called P, and it's at the location 1, 1, 0. To the plane containing the points 2, 1, 0, which is called Q, 0, negative 1, 1 called R, and 1, 0, negative 1 called S. The names don't sound really important, but they wanted us to have names. So, okay, we'll throw names in. So what do we have? Well, we have a couple of things. We have our points here, Q. I'll put that 2, 1, 0. We have R, which is 0, minus 1, 1. And we have S, which is at 1, 0, negative 1. And these points lie somewhere in dimension 3. We don't need to worry too much about exactly where they are right now. It doesn't seem to be that important. But they're in some plane. So there's some plane that contains all 3 of these points. And then, in addition, somewhere out there, there's another point. And that point is called P. And it's at the point 1, 1, 0. And what we're looking for is the distance. Now, it's important to remember what we're looking for. Since we're looking for a distance, our final answer should be a number. So we are after this distance here. Distance to the plane. Now, what can we do? Well, we'll make it simple on ourselves and say, hey, if we want to find the distance to the plane, we just need to know if there's a formula for it. There's a lovely formula for it. So here's our lovely formula. So if I have a point, and I'll call it x, x1, y1, z1, and I want to go to the plane, ax plus by plus cz equals d, then the formula says you plug it in. So it's like you plug this point into the equation, and it's not going to be equal, unless, of course, you're already on the plane, which is very boring. But you look at the difference. ax1 plus by1 plus cz1 minus d, and you divide by the square root of a squared plus b squared plus c squared. Okay, so that's our generic formula for the distance from a point to a plane. In order for us to use this, we actually need to know the plane. We already know the point, so that's easy, but we don't know the plane. So it sounds like it's going to be an intermediate step is figure out what is that plane. Okay, so let's think about what we have. We have 3 points. Now, it makes sense that if I have 3 points, that should determine a plane. But when we think about a plane, what do we need? We need a point. Okay, plenty of points. We've got Q or R. Pick a point. It doesn't matter. And a normal vector. Ooh, now the normal vector, that does matter. We got to figure that out because it's not given to us. So how do we construct a normal vector? Well, we have to find somehow a vector which is perpendicular to the plane. Now, one of the things you can do is start asking, can I find some vectors in the plane? And if I can use them to construct the normal vector. I need to find 2. But they have to be 2 vectors which are pointing not parallel. So they have to be pointing away in different directions. Do you see a way to make some vectors? There's actually a lot of vectors. What we can do is pick a point. It doesn't really matter what point you pick. Let's go from R. And let's head out to the other 2 points. And now we're going to make vectors. Now, it's important that we make vectors. We can't start with the points and take cross product of points because cross product of points is nonsense. It doesn't work. You have to have vectors. So if you try to do 2, 1, 0 cross 0, negative 1, 1, forget it. It's not going to work. Okay, got to get our vectors. So think about the change. If I go from 0 to 1, that says we change by 1 in the x-coordinate. Negative 1 to 0, that's a change of 1. 1 to negative 1, down by 2. 0 to 2, okay, that changed by 2. Negative 1 to 1 is another change by 2. And 1 to 0 is a change by negative 1. All right, now we have 2 vectors in the plane. They're not pointing in the same direction. And our normal vector will be perpendicular. So if you think about, remember, the right-hand rule, when you take the cross product, you get something perpendicular. So if we were to take the cross product, it would point up, be perpendicular to both of the things that we started with. All right, so again, another cross product. And by the end of our session, you're going to be like, we did a lot of cross products today. Yes, because it's a fantastic way to make something perpendicular, and normal vectors are perpendicular things that we want. So we do 1, 1, negative 2, cross 2, 2, negative 1. So that will be I, J, K, 1, 1, negative 2, 2, 2, negative 1. I times 1 times minus 1, minus I. J times minus 2 times 2, minus 4j. K times 1 times 2 is plus 2k. And then 2 times 1 times k, well, that's minus 2k. 2 times minus 2 times I is minus 4i. Of course, remember, we're subtracting. So it's plus 4i. And minus 1 times j is minus j. But, of course, we're subtracting. So it really becomes plus j. So that looks like we end up with 3, negative 3, and 0. Now, we do our check. Dot products, right? 3 minus 3, 0. Good. 6 minus 6, 0. Great. Good. Now we found 2 things. Now we found our normal vector, right? It's perpendicular to both the ones we started with. And we say, okay, so what's our plane? Well, our plane would be the following. 3x minus 3y plus 0z. And it's okay. Oftentimes we don't even write that. I'm just trying to emphasize it's there. If we had just written 3x minus 3y, perfectly fine. Equals something. Well, what? Well, pick a point. Which one? Doesn't matter. Suppose we plug in 1, 0, minus 1. All right, we can. So it'd be 3 times 1 minus 0 plus 0. So this should be 3. and we're good to go. Now, of course, what should be true? We can do a check. And here's a check. Let's just check the other points and see if they also satisfy the equation. 0 plus 3 plus 0. 3, good. And here we have 6 minus 6 plus 0. Sorry. Haha, I was using the vector. Got to use the point. 6 minus 3 plus 0, which is 3. Good. So this definitely is an equation that all 3 points satisfies. Well, we can clean it up, right? You can see it. Everything there has a factor of 3. So a better way to write this is our plane. X minus y equals 1. Okay, so here's the plane. So now we can rephrase our question. What's the distance from the point 1, 1, 0 to the plane x minus y equals 1? Throw it into the formula. So here we go. We're plugging in x equals 1 and y equals 1 and z equals 0. Well, we get the following. So we're going to get 1 minus 1, because we plug in x equals 1, y equals 1, z equals 0. Well, it's already 0, so very zero-y. Minus d, minus 1. Divide by, don't forget taking the absolute value of that. And this is a case where my absolute value signs look suspiciously close to 1, so be careful. These are absolute values on the end. Divide by the square root, and here it's 1 minus 1, 0. So 1 squared minus 1 squared, 0 squared. And upstairs we see, it's the absolute value of negative 1, which is simply 1. And downstairs it is a square root of 2. So actually they're pretty close. It turns out that that point, 1, 1, 0, is close to the plane we started with. Well, this time, but who knows what happens next time? We'll find out when we do more problems. Of course, got to be familiar with the process. So this is a way, given 3 points, we can find a plane. Good, good. All right. Well, that's an idea so nice. Let's do it twice. So, part A, find an equation for the plane through the point. So we have 3 points. And here, again, different notation. You're going to see lots of different notation if you start reading lots of textbooks. You're probably thinking, I don't know if I want to read a lot of textbooks. Well, you probably don't have to. You really just want to get used to the idea of, what are the pictures? How do things fit together? And then be comfortable with the idea, hey, I can change notation, but the ideas underneath it are still fine. And if you're stuck with the notation, if you're like, if you change notation, I can't handle this anymore, then you haven't thought deep enough. You've got to get to the point where you get past notation, where you just say, look, you give me a notation to follow, and I can adapt. That's when you really become a master. So that's what you want to be able to do. So what do we have? Well, we have our 3 points. So we'll just do the same process. And of course, we'll go through it a little faster. So we have minus 2, 0, 2. We have 2, 1, 0. And we have the 1, 2, 1. And so we just pick a corner. Doesn't matter. We'll pick that corner. So here are 2 vectors in the plane. And we just start from our corner and we look at how did we change. Well, 1 to negative 2, negative 3. 2 to 0, negative 2. 1 to 2, positive 1. Then 1 to 2, 1. 2 to 1, minus 1. 1 to 0, minus 1. So there's our 2 vectors. Next up, we cross them. Because once we have 2 vectors in our plane, the cross product will give us something which is perpendicular to both, and the normal is perpendicular to both. And see, that's why it's so nice to be in dimension 3. Because I say, well, look, I have 2 directions, and I found something perpendicular to both. And if I have 2 things which are perpendicular to both, so in other words, the cross product is perpendicular to both, the normal is perpendicular to both, then that says these things have to be parallel, which is why we say it finds the normal, because the normal is a really bad word. It's anormal, right? It's just a matter of scaling. Okay, we're getting sidetracked. Finish the problem. Come on, let's do it. So what do we have? We'll have I, j, k, minus 3, minus 2, 1, 1, minus 1, minus 1. And, okay, well, here we go. I times minus 2 times minus 1, 2i. J times 1 times 1, j. K times minus 3 times minus 1, 3k. 1 times minus 2 times k, minus 2k, but we subtract it, so that becomes plus 2k. Minus 1 times I, minus I, but we subtract, so it becomes plus I. Minus 1 times minus 3 is times j, plus 3j, but we have to subtract it. And we end up with 3 minus 2, 5. And of course we check, because the one time that we don't check, we'll get it wrong. So we're always going to check. Minus 9 plus 4 plus 5. Good. 3 plus 2 minus 5. Great. It worked. It worked. So this is the normal vector to our plane. Now, we're not quite done with part A, but we're really, really close. So to finish off for part A, we say these are our coefficients of x, y, and z. So we have 3x minus 2y plus 5z equals something. And now we say that's our answer for part A. But what's the something? Well, to figure that out, we do a little bit of work underneath. And we pick a point. Doesn't matter. Let's pick a point with a 0 in it to save ourselves some work. 3 times 2, 6, minus 2 times 1 plus 5 times 0. And we say 6 minus 2 plus 0 is 4. And so, that's a 4. Now, here's a place where you can really, really check that you did it right. Just check the other points. 3 minus 4 plus 5. 4, good. Minus 6 plus 0 plus 10. 4. Perfect. So it's definitely the right plane. 100% we got the right plane. You don't even have to doubt. We know we got it. Now, for part B. Find the point where this plane intersects the y-axis. So it sounds like it's going to be a hard problem, but then we think about, well, wait a second. This isn't a hard problem because we know what the y-axis looks like. So for part B, we say y-axis is really just happening when x is 0 and z equals 0. In other words, I'm on the y-axis if the only thing that's not 0 is the y-coordinate. So, plug in x equals 0 and z equals 0, and we say, all right, on the y-axis, it has to be the case that 0 minus 2y plus 0 equals 4, or y is negative 2. But I already know x and z, and therefore 0 minus 2, 0. And that will be where we hit the y-axis. Good. That one wasn't bad at all. It was almost easy. Too easy. Well, don't worry. We'll have some ones to challenge us as we go along. There's a lot of fun ones coming up in the future. Well, let's try another problem. So, next one. Find the plane which contains the points 1, 3, 2 and 2, 1, 4, and also perpendicularly intersects the plane 3x plus y is equal to 5z plus 19. Okay, so let's think about the picture here. What do we have? Well, what we have is we're in space, and we have these 2 points. 1, 3, 2, and we have 2, 1, 4. Now, what can we say for sure? Well, we know that those 2 points are definitely in the plane because it's told that the plane contains those 2 points. And the nice thing, of course, is if those 2 points are in the plane, everything between those 2 points are also in the plane. So in some sense, we say, hey, there's this set of points here that have to be in the plane, namely the line that passes through those 2 points. Okay, so now we know that the line which passes through those 2 points has to be in the plane. Well, is that enough to figure out the plane? The answer is no, because what can happen? Well, you can think of it as sort of this way. So we have a line here, and then we have our plane. And you can imagine, and sorry, this is low tech, but you can still have a line, but you can twist the plane. So we are able to rotate the line around, the plane swings, but the line stays in place. So we don't yet have the plane determined. So we're trying to somehow figure out where should we end up so that the plane that we have is going to be perpendicular to some other plane. So we have to think about that. But we have something here. And now, what else? Well, it has to perpendicularly intersect a different plane. Whenever we see a word perpendicular, we start thinking like, ooh, this is going to start adding some conditions about things being perpendicular. In the back of our mind, we say there's going to be a dot product or a cross product. So we should start thinking about what do we have? Well, when are 2 planes perpendicular? So I have 2 planes. When are they perpendicular? Well, we kind of know when they're not perpendicular visually, but when do they form that nice 90-degree angle? And the answer is, we say, look, planes are perpendicular if their normal vectors are perpendicular. So now we say, aha. So we think about our normal vector. Now, we should have paused and said, what are we looking for? We're looking for a plane because it tells us, find the plane. What do we need to find a plane? Well, we need a point and a normal vector. Okay, so for the plane, we need a point and a normal. Now, the point, easy. Why? Because we have 2 to choose from. Pick one, doesn't matter. 1, 3, 2. Why? I don't know, I felt like it. Okay, the normal has to be the work. Now, but we say, hey, our normal vector for the plane we're trying to make has to be perpendicular to the normal vector for the plane we were given. So let's look at that normal vector. Now, of course, they've modified the way to write the equation for the plane to obfuscate a little tiny amount, but we're on to their tricks. We know how to figure this out. So the original plane that was handed to us could be written as 3x plus y minus 5z equals 19. And so the normal vector we can see is 3, 1, negative 5. So we say, okay, whatever the normal is, it's got to be perpendicular to this vector 3, 1, negative 5. And then we say, wait, hold on, there's that line. So you remember we said that there's a line in the plane. So we can use the direction of the line. That has to be in the plane. And the normal is always going to be perpendicular to anything in the plane. So we say, aha, okay, that gives us a second thing we're perpendicular to. So we pick a direction. It, again, doesn't really matter. So let's suppose we went from 1, 3, 2 to 2, 1, 4. So 1 to 2. It says we went up by 1. 3 to 1, down by 2. 2 to 4, up by 2. So 1, minus 2, and positive 2. Okay, so that's the vector that connects the 2 points. That's a vector in the plane, and therefore another thing our normal has to be perpendicular to. And now we're like, aha, this is fantastic. We have 2 things we have to be perpendicular to. Because once we have that, cross product comes in. So here we go. Yet another cross product. Well, like I said, we're going to get great at doing cross products by the end. So we'll do it here to the side. We have I, J, K, 3, 1, negative 5, and then 1, minus 2, and positive 2. All right, so, and I just am scanning to make sure I have it all set up. I haven't made any mistakes yet. Looks pretty good. Looks reasonable. Here we go. I times 1 times 2, 2i. J times minus 5 times 1, minus 5j. K times 3 times minus 2, minus 6k. 1 times k, that's a k, but remember we're subtracting it. Minus 2 times minus 5 times I, that's 10i, but we're subtracting. 2 times 3 times j is 6j, but we're subtracting. So you end up with minus 8i minus 11j minus 7k. Or normally we'd write that as minus 8 minus 11 minus 7. Okay, all right. Very negative. We can change it. Look, if you don't want all the negatives, just scale everything by a minus 1. You can use that. You can use any scalar multiple of what comes out, because we're not after the normal vector, because there isn't one. We're after a normal vector. So if you want to scale it, scale it. Life is fine. Why not? Well, we have to check. So our check, 24 plus 11, 35, minus 35, 0. 8 minus 22, that's negative 14, plus 14, 0. Good. So that is our right cross product. So that, well, plus scaling. So therefore, our normal vector, we can use 8, 11, 7. Now we've done all the hard work. And it's a little bit of work, and we'll be finished. So what's our little bit of work? Well, we have our coefficients. The coefficients are the entries in the normal. So we know our plane looks like 8x plus 11y plus 7z equals something. And now the question is, what's the something? How do we find it? Good question. So to find it, do a little bit more computation with the point. 8 times 1 is 8. 11 times 3 is 33. And 2 times 7 is 14. So we get 8 plus 33. Well, 8 plus 33 is 41. 41 plus 14 gives us 55. And we're done. Now, one thing we can do as a quick check, sanity check, just check that the point 214 also is in there. You know, because it should be a point in the plane, and we didn't use it directly. So let's see, 16 plus 11, that makes 27 plus 28. 27 plus 28, yeah, it's 55. That's a good sign. A good sign that we're doing things right. Well, yes, because we're using geometry, and that's making sure we're on the right track. Okay. Good. Well, let's do another problem. So, find the plane that contains the point 103, 021, and never intersects with the line x equals 14 minus t, y equals 27 minus 2t, z equals 3t minus 137? Wow. Now, we have to think about, what does it mean to say that we never intersect? So visually, we have a plane, and so if we don't intersect with the line, it means our intuition is that the line is parallel to the plane. Okay, so that's good, but think about what it really talks about in terms of direction. If you either push the line down into the plane or push the plane up into the line, it doesn't really matter. Let's push the line down into the plane. What's true about the direction of the line? The direction of the line is inside the plane. So the direction of the line is coming from inside the plane. Okay, it sounds like one of these, sometimes you see horror movies. The call is coming from inside the house. See, The direction is coming from inside the plane. It was in the plane the whole time. All right. So what do we have? Well, this really tells us something about our direction. The direction of the line has to be perpendicular to the normal. Okay, so this last part right here really is just a fun and fancy way of saying our normal vector for our plane has to be perpendicular. And if I haven't said it before, this symbol is just a shorthand symbol for perpendicular to, and now read off the coefficients for t. -1, -2, and 3. And notice these numbers here, the 14, the 27, the 137, they're all red herrings, meant to intimidate us, but we won't be intimidated. It turns out they're not needed for the problem at all. They don't give us any insight. So, okay, well that's great. Now we say perfect. We know something about the normal vector. It's perpendicular to that vector. But we also know there are 2 more points. Well, so let's talk about that. So we have the point 1, 0, 3, and we have the point 0, 2, 1. So if those are both in the plane, then it has to be the case that the line connecting them is also in the plane. So we say, great. Now let's just draw the vector between those two. And what's that vector? Well, this vector between the two, if you can draw it straight, well, it's go up by 1, down by 2, up by 2. 1 minus 2 plus 2. And we see, aha, the normal vector for our plane is also going to be perpendicular to this vector we just discovered, 1, -2, +2. So now we have 2 things that our normal vector has to be perpendicular to. This is our ideal situation, and now we say cross product, and away we'll go. So here we go. IJK. -1, -2, 3. 1 minus 2, +2. And we'll get -4i plus 3j. Whoops, j, not k. Sorry about that. Plus 2k. Then minus 2k plus 2k minus 6i. So that really becomes plus 6i minus 2j becomes really plus 2j. So it looks like 2, 5, 4. I did that kind of fast. I'm a little bit worried. Well, what do you do if you're worried? You check it. That's what you always do, right? And here we go. -2, -5. -2, -10, -12, plus 12, 0. 2, -10, plus 8, 0. So that is right. So this is what we can use as our normal. As to the plane. And now we're like, perfect. We have a normal vector. So that becomes our coefficients. 2x plus 5y plus 4z equals something. Now we just have to figure out, well, what's the something? Pick a point. 0, 2, 1. So plug in 0 plus 10 plus 4. Because we do it in 0, 2, and 1. 0 plus 10 plus 4 gives us 14. Okay. Now, if we're paranoid, which hopefully I'm making you be a little bit paranoid to check your work, plug in 103. 2 plus 0 plus 12 is also 14. So that's our plane. It contains our points, and it's going to never hit that line because we made sure that the direction of the line is in the plane. So that means that the plane is essentially parallel to the line. Good stuff. Good. Well, we move on. on to another problem. Woohoo! More problems. So, find the point on the line x equals 2 plus t, y equals 3 minus t, z equals 3t, closest to the point 3, 4, 5. So we have a line, and we're after a point. Now, this is a little bit different than what we've done before, where we said, well, find the distance from the point to the line. We said, look, we're not after the distance, we're after the point. So, it's a little bit different, but that's all right. Well, how do we proceed? We have our line, and here's our point. 3, 4, 5. And what do we want? Well, we want to find that point right there, the one that's closest to it. So we start to think to ourselves, how can we go about doing this? Well, there's actually lots of ways to do this, but let's just think about something fairly simple, which is to say, let's introduce a plane. And you're looking at this and saying, there's no plane in this problem. Exactly, it needs a plane. Well, of course, not every geometry problem needs a plane, but we can think of it this way. We say, here's a line, and here's this point. Once I have a line, it's very easy to talk about the planes which are perpendicular to that line. There's a whole bunch of planes that are perpendicular to that line, and we just say, well, let's move our plane around that's perpendicular to just the right spot. You might say, well, what do you mean by just the right spot? So that our point is on that plane. So we can do that. That's actually not so bad, because it's really easy to find a plane if we have a normal vector, and the direction vector of the line is the normal vector to the plane. So we say, all right, make a plane. So we're going to make our plane, and our normal vector is going to be the direction vector of the line. All right, that's what we just talked about. And that is, well, read off the coefficients for t. We have 1, -2, +3. Okay, so now we have our normal, and now our point, whoop, forgot my parenthesis there. Our point, well, we want to have our plane be 3, 4, 5. Okay, why? Well, we're adjusting our plane so it has a point 3, 4, 5. Okay, if we do that, well, that's not so bad. We get at 1, -2, 3, those are our coefficients. So x minus 2y plus 3z equals something. So to figure out the something, we use our point. And our point here is 3, 4, 5, so 3 minus 8 plus 15. Well, 3 minus 8 plus 15 is 10. Okay, so there's our plane. Now, what's nice about this plane? Well, if we try to add it to our picture here, what's nice is our plane is sitting right here. It's perpendicular to this line, and it contains the point 3, 4, 5. So it also contains one other thing. It contains the point we're after, and that's the whole key. The plane that we introduced also contains the point we're after. So now we've changed our problem. It says, well, we need to figure out when does this plane and our original line intersect. Great, we can do that kind of problem. So what do? Well, we say to ourselves, we put in x, y, and z in for x, y, z. So 2 plus t minus 2 times 3 minus 2t plus 3 times 3t equals 10. And what do we get? Well, we get t, then a plus 4t plus 9t, 14 times t. And then we also have 2, and here is minus 6. So that would be minus 4, move it across, gives us 14. And so that tells us t should be 1. So when we plug 1 in to our equation, what do we get? Well, that tells us we get to the point 3, comma, 3 minus 2, 1, comma, and then 3. So the point 3, 1, 3. That's the point on the line. Namely, it's the point when t equals 1. And it's the closest point we have to the point 3, 4, 5. And that's it. We're done. Wow. Great. That wasn't so bad. That was kind of fun. We should have more problems like this. All right. So there you go. On to some more problems. So let's do our next problem. Give the equation of the sphere with center minus 1, 2, 3, which is tangent to, and when we say tangent, we mean touches. That's what the word tangent means, is to touch the plane. 4x minus 5y plus 2z equals 7. Okay, well, let's see. What can we do? What can we do? Well, if we think about it, we say we have our plane. So here's our plane. And we have our center of our sphere. Our center is up here. And we say, all right, well, our sphere, we'll do something like this. Now, if we need a sphere, one of the things we can think about is, what do we need? Well, when you have a sphere, you need a center. We've got that, and a radius. So we say, aha, what is our radius? Well, our radius would be the distance down to any point on the sphere. Well, let's take it to the point of tangency, that one special point. So we say our radius is equal to our distance to plane. Okay, so now it's just saying, what's the distance to the plane? It's the distance formula. Now we have some other options. Another option is we can do what we've done in similar problems, which is we could actually find the closest point on the plane and find the distance between those 2 points. Perfectly fine. You can do that. We just need an option. Since we've explored other options before, we'll let you take a look at other problems, right? You should take a look. There's some good problems we've done today. So let's recall the distance formula. So the distance formula looks like the following. Absolute value of ax plus by plus cz minus d. Divide by the square root of a squared plus b squared plus c squared. Okay, well, yeah, that's what the distance formula is. Okay, so we have all the pieces. A, B, C, these are the 4, negative 5, 2. The D is the 7. The X, Y, Z, that's your minus 1, 2, 3. So it's like we plug minus 1, 2, 3 into this side. So if we do that, we'd have minus 4, minus 10, plus 6, and then subtract your D, subtract 7. So that's your 4x minus 5y plus 2z minus d over the square root of 4 squared and 16, negative 5 squared, 25, and 2 squared, 4. So, what do we have here? We have a lot of stuff going on. 4 minus 10, that's minus 14. Minus 7, that's minus 21. And then we add 6, minus 15. Well, another way to say that is to say, when we take the absolute value, it's just 15. That's not so bad. And here we have what? Square root 16 plus 25 plus 4 is the square root of 45. Now, kind of interesting here, little side note, turns out, true story, 45 is 15 times 3. It's true, it's true. And now, if you clean this up, you see that the 15 upstairs is really a square root of 15 times the square root of 15, and you can cancel off, like that, and which is good. So we say Great. So now we have a square root of 15 over a square root of 3. But wait, 15 is 5 times 3. So it's really a square root of 3, square root of 5 over a square root of 3. So more. So we end up with square root of 5. So that's our distance. That's a nice number. Ah, that's good. Whoever wrote this wanted us to have a nice number because they care. Well, of course they care. Calculus instructors care about all their students. We love our students. We want them to be happy. And of course, we know that when they have nice numbers, they're happy. Now, we're not done because that's the radius. We need to write down the sphere. And so, what do we end up with? Well, our equation would be x minus 1, so really x plus 1 squared, y minus 2 squared, z minus 3 squared is square root of 5 squared, which would be 5. Okay, and we're done. We're done. Now, like I said, there are other ways you could do this problem, namely find the actual nearest point. So in other words, we could find that point, and then we'd be fine, because once we have the point, just use the distance formula. You could probably even attack this problem in a purely algebraic way. Well, as fun as that is, let's focus on geometric for right now. All right. All right, on to our next problem. Give the equation of the sphere. Wait, what? Again? Well, hold on. With center 2, -1, 4, and which is tangent to, touches at one point the line. Ah, okay, it's changed up a little bit. X equals 3 plus 4t, y equals 1 plus 3t, and z equals 4 plus 5t. Okay, well, think about the picture here. So we have a line. So here's our line. Whoop. And we have our point. Here's our point. And now, what are we after? Well, we want to have our sphere just big enough so that it reaches out and touches that line at a single point. Okay, so maybe it looks something along the lines of the following. All right, so there we go. Now, when we think about a sphere, what do we need? Well, what we need is the center. Done. Got that. And the radius. Got to work on that. So let's think about finding out what the radius is. So we need to think about what's this distance here. That will be r. And we go from our center to our point of tangency. Why there? Well, we can go from our center to any point in the circle, but we should say, let's get things which are involved in the problem, which makes sense to have the tangency. Okay, good. So how can we solve this? Well, we can solve it by a couple of different ways. We've actually talked about, look, if I have a point, I can find the closest point. And then once I have the closest point, it's the distance between 2 points. So that's one way to solve it. We won't do it that way. We're going to just say, hey, there's a formula that's about distance between a point and a line. So we'll use the formula. We'll recall what it is. And then we're going to do something completely algebraic. Wow, really? You can solve this all algebra? Oh yeah, it's good times. But first, let's talk about distance. So what do we have? Well, let's go into our general setting. If we have our picture here, here is a point, and we'll call it P. That's our point we're trying to get to. Down here is Q, and there's a direction vector, and I'll mark it here, a different color just so we can see it, and that direction vector is V. Now, what are we looking for? Well, we're looking for the distance. So the distance is going straight down to the line. So that's at right angle. All right, so what's the formula? Well, the formula is the following. We have that our distance is going to be the product the cross product of the vector from Q to P with the vector V over the vector V, but everything has a magnitude. Okay, so take a cross product, take the magnitude, divide by the magnitude. Now, it kind of feels like a projection. Remember how projection says, I want to know how much of this vector points in the direction of some other vector. And so you say, okay, so we project down, and then we take a look. Somehow we want to do the opposite. We say, well, look, I don't want to know how much points in that direction. I want to know how much points in a perpendicular direction. And so we say, well, if you want to be perpendicular to V, cross with V, guaranteed you're going to be perpendicular to V. So it actually makes sense to use the cross product to say, hey, I want to know what's happening in a perpendicular direction. And so we say, all right, well, what do we need? Well, we need to have all this data. So let's go through and fill in what we know. Well, we know our center. That's our point we're trying to be close. So that's the point 2, -1, 4. We know our point Q. That's the point on the line. Now, there's actually many points on the line. So what we do is we say, hey, 3, 1, 4. Just read off the constants for the x, y, and z. So there we go. 3, 1, 4. How about v? Again, we can do that. So we read off the coefficients for the t. 4, 3, 5. Good. You see, we want to get to the point where we're so comfortable with lines. It's like we're on a first name basis. Hey, Liney, how you doing? Hey, what's your direction again? Ah, you don't need to tell me. I see it. No problem. No problem. Of course, there's still one more vector we have to do. We have to have the vector that goes from Q out to P. So we look at our change. How are we changing? Well, we went from 3 to 2. That's down by 1. 1 to -1, down by -2. 4 to 4, no change. All right, well, good. Now we have our pieces. Step 1, find the cross product. So let's do step 1. Here we go, cross product. So if we take QP, QP, not QR, QP cross V, that would be IJK. Then Q to P, -1, -2, 0. V, 4, 3, 5. 4, 3, 5. Now I'll tell you, it's happened to me in the past when I've been doing these problems, and I haven't been paying attention, and I would do something like, instead of doing the 4, 3, 5, and I should really make that look like a vector. Make those angled braces even more angly. Sometimes I'd be like, oh, it's 3, 1, 4. No. Pay attention. Don't make silly little mistakes like I make. Make different silly mistakes. But what do I mean? Make sure that the vectors you're using the vectors and not points, because sometimes your figure gets crowded and you start to confuse. Okay, wait, which one is which? So pay attention. Make sure it's like, okay, I grabbed the vector, I got what I needed. So we continue. All right, so what do we have? Well, I times -2 times 5, -10i, j times 0 times 4, no j, k times -1 times 3, -3k. 4 times -2 times k is -8k, but we're subtracting, so it really becomes a +8k. 3, 0, and I becomes a 0i. Of course, we subtract it. And 5 and -1 times j, -5j, but we subtract, so it becomes +5j. So we end up with -10, 5, 5. Well, of course, we check because we're paranoid. We know the first time we don't check, we're going to make a mistake. So 10, -10, +0. Good. -40, then there's a plus 15 and a plus 25. 0. Perfect. Perfect. So now we're most of the way there. In fact, we can save ourselves some work. Because notice what we have. Everything has a factor of 5, so let's pull it out. 5 -2, 1, 1. Now, I'm not changing the vector. I'm just rewriting the vector in a convenient way so that it's 5 times some other scaling factor. We're allowed to do that. That's okay. Perfectly okay for us to do that. All right. Well, good. Now, what do we have? Well, our radius is what? So we have our radius of our sphere is going to be equal to the distance to the line. All right. And that is going to be, according to this, the magnitude of 5 minus 2, 1, 1, divided by the magnitude of v, 4, 3, 5. Okay, well, here you can just take the 5 out. So it's 5 square root 4 plus 1 plus 1, because negative 2 squared plus 1 squared plus 1 squared. Downstairs, square root of 4 squared, 16, 3 squared, 9, 5 squared, 25. Well, that's 5 times square root of 6. Downstairs, we have 16 plus 9 is 25, plus another 25 makes square root of 50. Well, look, square root of 50, that has a factor of 25 in it. So you can think of this as 5 square root of 6, pull out the 25, 5 square root of 2, the 5's cancel. All right, beautiful. Almost like whoever wrote this wanted us to have a nice answer, because they did. Square root of 6 over square root of 2 simplifies to give us square root of 3. So that's our radius. So, final answer, well, we have our center. We already started with that. So our answer will be x minus our x coordinate squared plus y minus our y coordinate. So y plus 1 squared plus z minus our z coordinate squared is our radius squared. Square root 3 squared makes it 3. All right, and we're done with geometric. But I said, let's do this one also algebraic. Now you're probably thinking, can you actually do a problem completely algebraic? And the answer is sometimes, yeah. Yeah, you can. So I'm going to cover this up so I'm not tempted to start thinking geometry. And we're going to think about what we have here. We say to ourselves, well, what don't we know? We don't know r. Okay, that's the true story. So, but we do know that our formula for our sphere will look like x minus 2 squared plus y minus minus 1 squared plus z minus 4 squared equals r squared. So once we figure out r squared, we're done. Okay, we also know our form. So we have our x, y, z. So let's replace x, y, z by these parts. 3 plus 4t, 1 plus 3t, 4 plus 5t. Okay, so what do we have? We have 3 plus 4t minus 2 squared plus 1 plus 3t plus 1 squared plus 4 plus 5t minus 4 squared equals r squared. All right, now let's keep going. Well, this would be 4t plus 1 squared plus 3t plus 2 squared plus 5t squared. Some good news finally. Equals r squared. Now, expand. So we get 16t squared plus 8t plus 1 plus 9t squared, right? You square the first term. Don't forget the cross term. This one is probably the tricky one. You know, it's a squared plus 2ab plus b squared. So here it would be 12t. That's probably the hardest part in this computation. Everything else, not so bad. And here we go. Now at this point, you're probably thinking, I don't know if I'm a fan of algebra. Bring back geometry. I totally know how you feel. But let's finish it up. We're actually closer than it might look. What do we have? Well, what we have is a lot of stuff. Let's group things by t. Now, why t? Well, t is really the thing that varies. R is just a number. So if we group things by t, we have 16 plus 9 plus 25. Well, 50 t squared. 8t plus 12t is 20t. Plus, then we have 1 and 4, and then the r squared we bring across. 5 minus r squared equals 0. Now, what do we see? We see a quadratic equation. So, we stop and we think about ourselves, okay, what's true about quadratics? How many solutions are there? Well, the answer is, if we think of this, we say, look, we can't have complex numbers. That just doesn't make any sense. So what we end up saying is that there are going to be 0 solutions, 1 solution, or 2 solutions. That's it. Because when we have a quadratic, it has to be 0, 1, or 2. So what do they correspond to in terms of geometry? Okay, so there's a little bit of geometry. So 0 solutions says what? We completely miss the sphere. Nothing works. 2 solutions says what? You have your sphere, but you pierce kind of through the middle. So you hit your sphere twice. We want there to be just 1 solution. So that's what we're looking for, is the 1 solution setting. So we say to ourselves, okay, what would make us have just 1 solution? So now we turn to a little aside and say, let's recall the quadratic formula. Remember, if you have ax squared plus bx plus c equals 0, then you get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So, if we want just 1 solution, what needs to happen is that this part right here, this b squared minus 4ac, that has to equal 0. So let's just figure out when that's true. So here we go. So we have, this is our a, b, and c. So b squared, 400, minus 4 times 50, that's 4 times a, times c, 5 minus r squared, has to equal 0. So in order for us to have just 1 solution, which means that we only touch the sphere once, that has to be true. Now, this is 200. That's great for us, because that means we can divide everything by 200. So it becomes simple. 2 minus 5 minus r squared equals 0, or 2 minus 5 plus r squared equals 0, or r squared is 3. So we can take this 3 here all the way back to the beginning. Say now we know what r squared is. So our final answer, x minus 2 squared plus y plus 1 squared plus z minus 4 squared is equal to 3. And we're done. So that's a way to do the problem completely algebraic, with only just a small smidgen of geometry to understand what does it mean to talk about there's no solutions, 1 solution, or 2 solutions. It's amazing. We get the same answer. And it's kind of cool how you're like, oh, there's these different ways to do these problems. And if I do it this way, what's involved? If I do it that way, there's different ideas. But in the end, we agree. And it's just, it warms the soul to see these beautiful ideas blending together. All right, well, we've got more ideas to come, so we forge ahead. All right, another problem. Given 3 points, x1, y1, z1, x2, y2, z2, and x3, y3, z3, excuse me, the centroid of these points is defined in the following way. So you add each coordinate up and divide by 3. So it's kind of like the midpoint. Remember the midpoint, how that works? If you had 2 points, you said, well, what's in the center? Well, you said, well, add the coordinates and divide by 2. Well, now what we have is we have the following situation where we have 3 points here, somehow in 3-dimensional space, and we're saying, well, we're looking for the center in some sense. So you can see the word centroid looks a lot like center. So there's actually lots of different kinds of centers. When you have a triangle, there's all sorts of varieties of ways to talk about what the center is. There's literally hundreds and hundreds of ways. There's a whole online site dedicated just to saying, here's a different way to think about a triangle center. And so you can even create new ones. It's a fun pastime. So what you do is you weigh them so that somehow it's like, well, each one contributes. So your centroid is somehow in the center. Okay, in some way, according to the formula. All right, now, what are we asked? Find the line which passes through the centroid of these points, and we're given 3 points, and is also perpendicular to the plane containing these 3 points. So, in some sense, you could almost think of it in the following way. If you were to take these 3 points that we have here, you could even just say, well, let me make the triangle. And it's like, all right, so I go out and I buy my triangle making equipment, and I say, okay, I have my triangle. And now what we'll do is we're going to take our triangle here in space and take a line. And that line is going to pass right through that center of the triangle. So our picture here is we have this line coming through. It pierces at the centroid, comes back out the other side, such that it's at a right angle to the triangle that we've just formed. All right. Well, we're looking for a line. So we start thinking to ourselves, if we need a line, well, we need a point, and we need a direction. And those are the 2 pieces that make up every single line. So every time we see a problem that says, find the line, and this problem says that. It literally says, find the line. So we know our answer should be a line. So we start thinking, okay, let's find a point. Let's find a direction. So what's our point? Well, the point is we use the centroid because it says it has to pass through the centroid. So we have our 3 points, 1, 4, 2, 7, -6, 3, and 1, -1, 1. So our point, well, we add up the x coordinates, 1 + 7 + 1, divide by 3. Add up the y coordinates, 4 - 6 - 1, divide by 3. And add up the z coordinates, 2 + 3 + 1, divide by 3. And if we do all of that, let's see, we get 9/3, 3. Here we get -3 over 3, -1. And here we get 6/3, which is 2. So there's our point. We're halfway done, right? Because we only had to find 2 things, and that's one of the 2 things that we have to find. So now we have to do the other half. Okay, so what's the other half? The direction. And we see, perpendicular to the plane. See, this is a direction description because we're talking about, well, there's a plane and we're perpendicular to it. So we're like, all right, so I have to be perpendicular to a plane. And when we see the words perpendicular to a plane, we say that really means a normal to the plane. So that's sort of our mindset. Now when we start thinking about normals, we start thinking, well, how can we find a normal? Once we have several points in a plane, probably the easiest way to find the normal is say, let's start with our points and let's make vectors in the plane. And once we have vectors in the plane, we start crossing them. 2 vectors crossed in the plane give us a direction perpendicular to the plane. That means we've got a normal vector. So here we go. Our next step, we pick a point. Well, let's pick this corner, and we're going to find our 2 vectors coming out. So from 1, -1, 1 to to 1, 4, 2. How did we change? Well, no change. Okay, 0. Up by 5. All right, that was a good change. Up by 1. So this vector is the vector 0, 5, 1. And then we're going to find another vector and take the cross product. Well, again, from the same corner. By the way, it doesn't have to be the same corner. You could pick now this corner and go out. We just need 2 vectors in the plane. It doesn't really matter which 2. As long as they're not parallel vectors, life is good. 1 to 7, 6. Minus 1 to minus 6, minus 5. 1 to 3, 2. All right, so we found a vector and another vector, 2 vectors, and away we go. So, cross product, here we come. I, j, k, 0, 5, 1, 6, minus 5, 2. All right, so 10i plus 6j and 0k. All right, and then in the other direction, minus 30k. Wow, that's a lot. Remember, it's 30k, but we subtract. And here, it's going to be minus 5, so it really makes plus 5i, and then nothing for j. Subtract that. So it looks like 15, whoops, I said 15, I wrote 16. That happens. You got to pay attention. 15 and 6 and negative 30. All right, well, what do? Well, we always do. We check. 0, 30, minus 30. Good. 0. Here, 90. Minus 30, minus 60. Good. We did it right. We got the right cross product. Okay, well, now what? Well, that's going to be our direction. Now, of course, we can pick a different direction. What else could we do? We could scale it. See, all these numbers are multiples of 3. So we could pull out a factor of 3. So 3, and here we could have 5, 2, negative 10. And now we can say, look, this is normal vector as well. 15, 6, negative 30 is as normal as 5, 2, negative 10. In the sense, they're both perpendicular. And that's what we really mean when we have normals, just perpendicular. So that can be the direction of our line. So there we go. Our direction is 5, 2, negative 10. If you'd use 15, 6, negative 30, still a correct answer. Remember, lines are not unique. There's many ways to write a line. So we can both do a problem and get to an answer that looks very different, but when we dig deeper, we say, oh, the direction vectors are the same, and hey, our points are both on the line. We both have a correct answer. So keep that in mind. Don't start being like, it's not exactly the same. I'm doing it wrong. Be like, oh, it's not exactly the same. Let's just check anyways. Oh, we're okay. Phew, good. All right. So we're ready to put it all together. So we get x, y, z, because it's a line. So use our points. 3, 1, minus 1, 2. 3, minus 1, 2. Then we have plus 5t plus 2t and minus 10t. And that is our answer. So that is the line. It passes through our centroid, which is good because we have to pass through our centroid. And it is perpendicular to the plane, which is also good because that's the other thing that had to happen. All right. Well, great. Good. We're making good progress. We're getting good at doing these types of things, right? Now, in some sense, what's the interesting part about this problem? Well, sort of the fun part about this problem is they handed us a new definition, which is the centroid. And they said, okay, here's a new definition. Now use it. So we're getting to the point where we're like, oh, all right, we'll just use it. We don't have to be like, oh my gosh, I've never heard about this before. I can't do it. We say, oh, okay, something new. That's fine. Let's figure it out and let's go with it. And we want to be comfortable with seeing new things. The world is full of things we've never seen before, so we don't want to panic whenever we see something new. we sort of calm ourselves. Relax. This often happens in exams. People are taking exams and they see a problem. They're like, oh my gosh, this is not identical to a problem I've ever seen before. Okay, I guess I just won't answer it. It's a terrible strategy. I don't recommend it. What's better is to say, oh, how interesting. It's not quite like anything I've seen before. This will be fun. And attack it like a puzzle to be solved. Once you have that mentality, things get better. A lot better. All right, good. Okay, on to another problem. The following two lines are intersecting. So we have x equals 1 minus t, y equals 2 plus t, z equals 3 minus 2t, and then there's another one, x equals t, y equals 3 minus t, and z equals 3 plus t. Find the line which goes through the intersection point and is perpendicular to both given lines. All right, well, now, what makes this one interesting? Here's something we have to be careful about. When we see this problem, we might look at this and say, hey, I see t's here, and I see t's over there. A t is a t. So it must be that they're the same, which is wrong. And so here's the thing we have to be really careful about. And I know that we look at and you hear somebody say like, these t's are different t's, and you're like, but it's the same symbol. And I know, and this is just such a weird thing. But what you should really be thinking about is as t varies in the first line, so in other words, I'm here in the first line, I trace out a collection of points. As t varies in the second line, I trace out a different collection of points. And so what am I looking for? Well, I'm looking for a point that's common. So the key here is that the common point did not happen necessarily for the same t. So this is sort of our word of warning. So we're going to write that down just because that's an important idea. So the intersection does not have to occur where our t's are the same. So in other words, it might be the case that it occurs for some value of t over on the first line, but a different value of t on the second line. So what do we do? Well, here's the safe thing to do. Change one of the names. So we'll change it to something else. So what do? We'll change it to something distinct enough that you won't confuse them, but maybe similar that you can use it. Now, of course, if we were trying to confuse ourselves, well, let's try it anyways. Expand our Greek alphabet. Use the tau. Tau is a great choice for t because they're both actually t's. See, tau is sort of like the Greek version of a t. So we'll say, let's change this to a tau. So tau has this sort of fancy squiggly on top. Okay, there we go. So now that's sort of the hard part about this problem, is being able to say, oh, let's separate these ideas from each other. All right, now we can dig into it. What do we say? Well, we say, look at the x coordinates have to be the same. 1 minus t has to equal tau. The y coordinates have to be the same. 2 plus t has to equal 3 minus tau. And the z coordinates have to be the same. 3 minus 2t has to equal 3 plus tau. Now here, if we look at this, we say, this is actually pretty simple, right? Because I can solve for tau in terms of t. Namely, it's right there. Pretty quick. Once I know tau, we can plug it in. So let's take our tau and plug it into our second equation. And that would lead us to what? Well, it leads us to 2 plus t is equal to 3 minus 1 minus t. And what do we have? Well, if we multiply it out, the minus through, we'll end up with 2 plus t. And it's actually a true fact. 2 plus t is indeed equal to 2 plus t. It doesn't give us any insight, though. Okay, so maybe we should have plugged it into there. Okay, what does that tell us? 3 minus 2t is equal to 3 plus 1 minus t. This is looking more promising because that becomes 4 minus t. Well, all right, we move the t across and we move the 3 across. So minus 2t plus t is minus t. 4 subtract 3 is 1. So we can say, all right, t should be minus 1. Now, if t is minus 1, tau should be 1 minus minus 1, which is 2. Let's check. So we come up here, and we plug in minus 1. What do we get? Well, we get 1 minus minus 1, 2. 2 plus minus 1, 1. 3 minus 2 times minus 1, well, that's 3 plus 2, 5. And if you plug in tau equals 2, you get 2, 3 minus 2, 1, and 3 plus 2, which is 5. Now you might be wondering the question, did we actually have to do that? Did we really need to plug it into both? And the answer is, it's better to do it. The reason I say it's better to do it is you want to actually verify that they did give you two lines which intersect, because they may have accidentally give you two lines which are skew. And if they did, whoops, something has happened. Or it may have been that you accidentally solved for the wrong t and tau. And he said, oh, well, maybe I should go back and check my work for solving for t and tau. So it's good to check it, because now we're confident. We see it works for both, and therefore we come to the happy conclusion that the common point of intersection is 2 and 5. So this here is the line, line goes to the intersection point. So this is our point on the line. So, progress. We found one of the two things that we need. Remember, whenever we're looking for a line, we always say, what are the things we need? We need a point, and we need a direction. All right, so we found our point, 2, 1, 5. But now we need our direction. So we transform gears and we say, where do we go next? So if we're looking for our direction, we say, okay, what are some things we know about our direction? Well, there's a key thing. We know something about it being perpendicular, and then we see this beautiful thing to both. So we say, oh, it's perpendicular to two things. Whenever I see something that says I need to be perpendicular to two things, something crosses through my mind. There's a cross product in our future. So what we need to do is say, well, what are the directions of the line? Well, we're getting pretty good with lines, and we can know how to read the directions of our lines. So we need to be perpendicular to the direction of the first line, which are the coefficients for the t. So that would be -1, +1, -2, and perpendicular to the second line. So that's +1, -1, and +1. Okay, so again, we should be able to take a line and say, let's read off our coefficients for our directions. -1, 1, -2, 1, -1, 1. Okay, now we're ready to do cross product. Again, we're going to get good at this. One way or another, we're going to get great at this. Okay, so we have I, J, K, -1, 1, -2, 1, -1, 1. So what does that give us? I minus 2j plus k minus k. Oh, that's interesting. Then we have 2i, but we got to subtract it, minus 2i, and then plus j, which, let's see, 1i minus 2i is -1, minus 2j plus j, -1, plus 1 minus 1 is 0. Okay, well, we have a 0. That's okay. It happens. What does that really mean when we have a 0? Well, what it means is, for instance, this is saying that there's no change in z, so that the line is somehow parallel to the xy plane, because there's no elevation change happening with our line. The z coordinate talks about the direction in the z direction, right? This is telling us how much z changes. there's no z change. So it's somehow parallel to the xy plane is what we conclude. Well, check our work. +1, -1, 0. -1 + 1, 0. That was easy, pretty quick. So here's our direction. Our direction is -1, -1, 0. Let's get rid of the minuses, right? Remember, we can scale, so scale by -1. 1, 1, 0. So we'll scale by -1 to get our direction. And that's just making note of what we're doing. We're not just doing things arbitrarily, we're doing things with purpose. So now we put it all together. And we say, all right, what's our line? X, Y, Z. And we're going to have 2, 1, 5. That's our point. Then plus t, and that's it. And z, there's no change. So 0t. Done. Great. Woohoo! Good. Well, let's try another problem. Find the line which passes through the point 3, -2, 4, and does not intersect either the plane 3x minus 2y plus, 3x minus y plus 2z equals 5, or the plane x plus 3y minus 5z equals 2. And we give our answer in parametric form. So, what's going on? Well, let's think about our picture here. We have two planes. And so we do a quick sketch of two planes. And so there's one of our planes. And then we have another plane, okay, that crosses at some angle here. Okay, so there's our two planes. And it might be nice just to help us visualize, there's a line that goes through their point of intersection. Okay, so we have these two planes which cross each other. And now what happens is that there's this extra point somewhere out in space. So let's say our point's out here. Here's our planes. What do we want to do? Well, we want to make sure we find a line that passes through that point and never intersects the other planes. How could we form such a line? Well, here's an idea. Think about this line of intersection. This is sort of something, if we can understand this, I think the rest of the problem is going to be pretty straightforward. What we could do is we could imagine if we take that line of intersection and pull it off the planes. Well, what happens? What happens is we end up, well, do I have a good color? This is a reasonable color. If I move my line of intersection up, okay, so I just pull my line of intersection off, what'll happen is, since it's off the planes, it will never intersect. You see, if I have a line in the plane and I pull it off, I can't have my line like, and all of a sudden go back into the plane. That's not how lines work. If it was in the plane and I pull it off, it's now going to never hit the plane again. So what is that telling us? Well, it's telling us that the direction of a line that doesn't hit a plane, or if you like, is parallel, it has to be a direction in the plane. So we say, aha, what we've really done here is say this line that we're after, it's like we took that line of intersection and just moved it so it went through our given point. That's what we're doing. But we're not going to do it quite that way. We're going to be a little bit smarter about it. Say, okay, we know we need a line. How do we know we need a line? Because it tells us, find the line. Okay, that's a pretty good clue. If it tells you find the line, follow the instructions. Follow the instructions. And I know you're saying, if I'm told to find a line, of course I would find a line. And I believe you. You're a great student. But I've had other great students before who weren't paying attention. They've put things like planes when it should be a line. So don't rush. Take your time. All right, so we know we're after a line, and so we say to ourselves, well, if we're after a line, we know we need a point and we need a direction. So our point, well, that's given to us, 3, -2, 4. So that's not going to take us very long to find at all. We found it. Okay. Our direction. Well, because we don't want to hit a plane, the way we avoid hitting a plane is that the direction of the line has to be a direction which could be in the plane. So if I have a line that doesn't hit the plane, if I push it down, that line is now in the plane. So we say to ourselves, aha, our direction has to be in both planes. Well, how is that useful? Well, it tells us that our direction has to be perpendicular to our normal vectors. So the normal vector for the first plane, 3, -1, and 2. I said -1. 3, -1, 2. And normal vector for the second plane, 1, 3, -5. So that's how we're going to find our direction vector, is we say, look, think of the geometry. The direction of the line has to be a direction in both planes. So that says the direction has to be perpendicular to both normals. Now we're perpendicular to two things. That's beautiful. We love being perpendicular to two things because we can use our cross product. So here we go. Once again. Once more to the breach, dear friends. Once more. So we have I, J, K. 3, -1, +2. 1, 3, -5. And we start. So we get 5i plus 2j plus 9k. Subtract minus k, so that's really a plus a k. Subtract 6i and subtract -15j. So that really means add 15j. So we get -1, 17, 10. Well, those are some weird numbers. That's definitely worthy of checking. So we check. -3, -17, that's up to -20, plus 20. Aha, good. -1, 3 times 17 is plus 51, so that gets us to 50. Subtract 50. All right, well, it just turned out they were strange numbers. That's okay. The numbers are what the numbers are. We don't have to be upset with them. We're just like, wow, what great numbers we get to work with today. All right, so we say our direction is -1, 17, and 10. So we now have our point. We have our direction. We put it together. We get our line. So our line will be x, y, z. Fill in the point. 3, -2, 4. And then the direction is multiplied by t. So -1 times t minus t. 17 times t. And 10 times t. And there we go. We got it. Nice. Good. Whew. I feel like we're going faster the further on we go. Well, of course, the further on we go, the more comfortable we are with thinking about the geometry of the problems. We've been doing a lot of these problems, so hopefully we're getting really good at learning to think geometrically. It's going to be a very useful tool. Very useful tool. Even if we don't do a lot of these problems in the future directly, the ability for us to think geometrically is important. Okay, so the next problem. The point 2, 1, 3 is the midpoint of the points P and Q. Okay, so we have a midpoint. If the point P lies on a line, then Q lies on some other line. So the question is, what's this other line? And give it in parametric form. Now, what's happening here? How should we think about this problem? It's kind of a strangely worded problem. But here's the idea. We have this line. So here we go. This is the line 5, 5, 2, 4. Okay, that is terrible handwriting. That's a 4. Plus t, 2, negative 3, 1. And now we have a point. Not just any point. It's this point right here. 2, 1, 3. And what's the idea? Well, the idea is if I have a point here, and here's my point P, well, what happens is I go through the midpoint and I reflect it, and now there's a point Q over here. And that's going to be true everywhere we go. So that as I go along this line and let P move back and forth, lo and behold, I'm going to end up tracing another line out on the other side. So the question becomes, what's this other line? So, all right, so that's what we have to think. Now, what do we have? Well, this is really going to test us more about midpoints than anything else. Do we understand how midpoints work? So the key for midpoints is to think about the midpoints are all about saying, look, average in each coordinate. So if we think about our points up here, we can say a typical point looks like what? This point really looks like 5 plus 2t, comma, 2 minus 3t, comma, 4 plus t. So that's how we'd represent it, sort of emphasizing more of it in parametric form. How does everything look, each coordinate look, in terms of a function of t? So now, what does the midpoint formula say? Well, let's imagine this Q here, this point, I'm going to call it x, y, and z. So the rule says, well, you add the first entries together and divide by 2. So you have x plus 5 plus 2t, divide by 2. And then the next one, you add these two together and you divide by 2. So y plus 2 minus 3t, divide by 2. And then in the last part, we have, comma, not a plus. These are commas. And the last one, z plus 4 plus t, and divide by 2. So that's our midpoint. But we know what our midpoint is. It is the point 2, 1, 3. So that equals 2, 1, 3. And now we're basically most of the way there. What's left? Well, we say, hey, these points are the same, so they have to match entry per entry. So this entry here has to be 2. The second one has to be 1. Third one has to be 3. And we go through and say, well, what does that tell us? Well, in the first component, we say, well, let's multiply by 2. And that tells us that x plus 5 plus 2t has to equal 4. In the second, y plus 2 minus 3t has to equal 2. Here, z plus 4 plus t has to be 6. Now rearrange. So, we solve for x. Subtract 5, subtract 2t. Minus 1, minus 2t. Here, subtract 2, subtract 3t. So the 2's cancel, and we're left with 3t. And the last one, subtract 4, subtract t, and you get 2 minus t. And there you go. So that, as P moves along this line, Q moves in this fashion. And here's the line in parametric form. So that's the answer. In fact, in some sense, this is sort of the ideal answer because it's really saying, look, how do the points P and Q actually interact with each other? It's not just that this forms the set of points, but if you give me a specific P, then I can tell you exactly what happens when you go across that midpoint, that halfway point. So, good. All right, well, a little different, right? And a little different makes it interesting. It's nice to be able to explore different problems. Okay, well, keep going. On to the next problem. So, find an equation for the plane that passes through the point 1, 2, 3 and is perpendicular to the line 1 plus 3t, 3 plus 2t, 1 minus t. Okay, well that's not so bad. Let's think about part A. Then we'll figure out part B. So part A says what? Well, we have to have a point. So we're looking for a plane, and what's true about this plane is that it has this special point here, 1, 2, 3. Now that's great news for us. That means we found a point on the plane. The other thing is it's perpendicular to the line. Now it means that somewhere out there, I don't know where, but somewhere there's this other line that's going to intersect this plane in a nice perpendicular fashion. And it's the line 1 plus 3t, 3 plus 2t, and 1 minus t. Well, if this gives us our point, what does the line give us? Well, it gives us something perpendicular. And perpendicular is just another way of saying that's something with the normal. Okay, so we have information about our normal vector. Well, what is our normal vector? So we say, well, the normal vector was going to be the direction of the line because it's perpendicular. And we read off the direction. It's the coefficients of t. So we end up with 3, 2, negative 1. Now we have our normal, we have our point. We can write down our formula for our plane. And we know we're looking for a plane because it says, find the plane. Okay, so that's how we know we're looking for a plane. So the 3, 2, negative 1, those are our coefficients for x, y, z. 3x plus 2y minus z equals something. All right, well, what's it equal? Well, to figure that out, plug in the point, 1, 2, 3. So if we plug in 1, 2, 3, what do we see? Well, we'll get, where are we at? 1, 2, 3. So 3 plus 4 minus 3, right? Because I plugged in x equals 1, y equals 2, z equals 3. Well, that's easy to solve. 3 plus 4 minus 3, that's 4. The 3's cancel. And now we're done with part A. Done. For part B, find the distance from the point 3, 2, 1 to the plane that we just found. Okay, well, how do we do that? Now we say, what's the new part? Well, now there's a point off the plane, 3, 2, 1, and the question is, what's the distance? All right, so how do we do part B? We'll use the distance formula. By now, if you've been following all the way through, first off, wow, that's amazing. If you've stuck around all the way through these problems, you're doing fantastic. You're going to have such an amazing ability to handle these types of problems. You should start teaching. You're ready. But okay. But the other thing, of course, is you've seen us deal with problems before. We can say, look, if I want to find the distance, there's lots of things I can do. We could actually find the nearest point and then say, what's the distance between the points? But we'll use the distance formula. So recall, our distance formula says what? Well, distance is the absolute value of ax plus by plus cz minus d divided by the square root a squared plus b squared plus c squared. Where a, b, c, these are the coefficients, 3, 2, minus 1. X, y, z is for our specific point. The d is, of course, this constant on the other side. So, in our case, we get, so imagine plugging 3, 2, 1 in. So 3 times 3 is 9. 2 times 2, 4. Minus z, 1. Minus our value for d, so that's 4, over the square root of 3 squared, 9, plus 2 squared, 4 plus negative 1 squared, 1. So, because when you square a negative, it's positive. Well, the 4's cancel. 9 minus 1 is 8. So you end up with an 8 on top. Downstairs, you get a 9 plus a 4 plus 1. Makes square root of 14. Well, if some teachers out there say, when you get to college, you got to be ready because their calculus instructors are going to make you want to make everything rational. And then you get to college and you're like, the calculus teachers don't care. We don't. Well, some do. But this is a great answer. But if you really are like, oh, I don't like square roots in the denominator, well, we can fix that. If you multiply by square root of 14 over square root of 14, then what will happen? Well, you get rid of your square roots downstairs. You end up with 8 over 14 times the square root of 14. You can cancel out a factor of 2, so you get 4. You get 4 over 7 times the square root of 14. And there you go. All right, good. That one's pretty straightforward. But again, slightly different. I mean, all these problems there's not like huge swings. Well, there's a couple of curveballs coming. But a lot of these have very similar ideas. It's just a matter of getting your intuition going. And hopefully you're seeing that we keep drawing pictures over and over and over again on these problems. Even if a picture is not exact, a rough picture gives us insight into how the problem is set up. And that's often all we need to get going, is insight into how things connect with one another. All right, well, we keep going. And let's go on and do another one. Oh, what? What are the odds? All right, we've got more to come. So, let L1 be the line segment joining 332 with negative 150. Let L2 be the line segment joining 143 with minus 321. L3 be the line segment joining 476 with negative 232. There's a lot going on here, isn't there? Now, find the unique plane which cuts these 3 line segments in half. Okay, so let's kind of understand what's happening here. And we're not going to worry too much about being exact picture, but we can think of, all right, we have a line segment that joins 2 points. And then somewhere else is a different line segment joining 2 different points. And then still somewhere else, there's a different line segment joining 2 other points. So we have some line segments out in space. Now, what are we looking for? Well, we're looking for a plane which is going to cut these in half. So I want them to go, my plane, to go through the centers. So somehow, if you can imagine here, that we can sketch a part of the plane as being containing this triangle. So there's this triangle, of course, but you extend it out. That's a plane, and it cuts them exactly in half. Okay, so that's not so bad. In essence, what's happening here is we're really just looking for a plane through 3 points. We've done that before. Now, what makes this fun is that there's this beautiful idea in mathematics. It's called the ham sandwich theorem. So what does the ham sandwich theorem say? Well, it says, suppose you have an object which has 3 pieces. So the example is a ham sandwich. So that's why it's called the ham sandwich theorem. And a ham sandwich, there's 3 important parts: the bread, the ham, and the cheese. Well, what it says is no matter how you form your ham sandwich, no matter like misshapen your bread is, because your bread slicer is just really poor, or maybe you have a weird block of cheese, no matter how that ham sandwich is put together, there's a way to take a knife and slice it exactly in half so that you produce the 2 halves have equal amounts of bread, equal amounts of ham, and equal amounts of cheese. So in other words, if I have 3 objects, I can slice 3 objects in half simultaneously perfectly. So in this case, the 3 objects are the 3 line segments, but of course, the ham sandwich theorem says it's even more interesting than that. So, okay, that's not so bad. It seems like there's a lot of work, but now when we dig into it, it's like, oh, I really just need to make sure I'm going through 3 particular points. So let's go through our points. Where are our midpoints at? So we'll start with L1. So we have our 3, 3, 2, negative 1, 5, 0. So we're going to have 3 plus negative 1 over 2, comma, 3 plus 5 over 2, comma, 2 plus 0 over 2. And that leads us to, well, okay, put parentheses here. We'll have 1, 4, 1. So let's put that point here. So here's our first midpoint, 1, 4, 1. Now we go around and say, okay, let's do our next one. So 1, 4, 3, and negative 3, 2, 1. So 1 plus negative 3 over 2. So I see 1 plus negative 3 over 2. 4 plus 2 over 2. And 3 plus 1 over 2. So let's see, 1 plus negative 3 is negative 2 over 2 makes negative 1. 4 plus 2, 6 over 2. 3 plus 1 is 4 over 2 is 2. Okay, so let's say that's this point here, negative 1, 3, 2. And now we go and finish up, and we do the last line segment. So 4, 7, 6, and negative 2, negative 3, 2. So we have 4 plus negative 2 over 2, comma, 7 plus negative 3 over 2, comma, 6 plus 2 over 2, which gets us to, well, we have 2 over 2, okay, 1. Here we have 4 over 2, 2. Here we have 8 over 2, 4. So 1, 2, 4. And that's our last point. 1, 2, 4. All right. Well, now we have 3 points, and we're ready to go. We have to find the plane through our 3 points. Great news. We've got plenty of points. What don't we have? A normal vector. So we say, well, if I have points, I can form vectors that are in the plane. So let's form some vectors in the plane. So what we'll do is we'll pick a corner. Doesn't matter which corner. Let's pick this corner down here. And we'll look at the 2 vectors heading out to the 2 other midpoints. Now, remember, we just need to look at the change. So negative 1 to 1, that's up by 2. 3 to 2, down by 1. 2 to 4, up by 2. Here, negative 1 to 1, up by 2. 3 to 4, up by 1. And 2 to 1, down by 1. So there we have 2 vectors which are in the plane. Now we're not after 2 vectors in the plane. Ultimately, we're after 1 vector which is perpendicular to the plane. But it's a good stepping stone because now we can cross product them together. All right. Wow. More cross product? Yeah, lots of cross product today. So here we go. So we have I, J, K. And make sure you copy vectors. Don't want to accidentally copy points because then we get the wrong answer. And we don't want the wrong answer. We want the right answer. Those are much better when you have right answers. So, okay. So where are we at? Wait a second here. I just want to check. Yep, okay, good. Everything looks good. All right. So we have 2i minus 2j minus 2k. Lots of 2's in there. And let's see. Subtract 2k. And then we're going to, normally it would be plus I, but we're subtracting, so minus I. And minus 4j. So that looks like a 1 minus 6 minus 4. Now, of course, we check because, well, I'm always worried. 2 All right. 2 minus 6, negative 4 plus 4, 0. 2 plus 6 minus 8, 0. Good. All right. Good. Now, that's our normal, and so we're almost there. So what do? Well, we say these are our coefficients, so we get x minus 6y minus 4z equals something. And whatever that something is, then we're done. So we just have to say, well, what is that something? What'll help us finish up? So we pick a point. Doesn't matter which point. Suppose I pick 1, 2, 4. So it'd be x equals 1, y equals 2, so minus 12. So equals 4, so minus 16. So it'd be 1, subtract 12, subtract 16. That's 1 minus 28, which would be negative 27. Okay, well, can we check our answer? We can, because we said, look, we picked 1, 2, 4. Pick another point and see if you're still getting negative 27. And if you don't, whoops, go back and check. Okay, so here we go. Minus 1, minus 18, that's negative 19. Minus 8 more is negative 27. That's great. 1, good. And then we're going to subtract 24, that's negative 23, and subtract 4 more. Negative 27 again. Good. So, everything looks good to me, and so we did it. Patience, patience. Work it through. You started with a lot of data, and it kind of felt overwhelming, but it's like, okay, dig into it. All of a sudden, not so bad. Just a lot of midpoints and working things through, and life is all right. Well, we keep going, because there are more problems for us to do. Woohoo! More problems. All right. So, our next one. Find the distance between the two lines. What? Between lines? Now that's different. That's really different. So we have to start thinking about, how do we go about finding distance between lines? Well, there's probably a formula, but let's think about the geometry. So we have two lines, and they're off from each other. So they might be at sort of some weird angle, and we say to ourselves, okay, what can we do? Well, here's sort of an idea. Suppose for a moment, just suppose, that we were to bring the lines together. What would be true? Well, what would be true is we'd have a plane. Now, at this point, how does that help us? Okay, maybe let's pause for a second, just for a second, and think about, what can we do? We can find the distance between a point and a line, and a point and a plane. So what we'd like to do is somehow reduce down to one of those cases. So why do I care about making a plane? If we think of the picture here, we could think of it as saying we have one line up here, and then somewhere else there's a second line underneath. So here's our second line that's underneath. There's this sort of skew line. Now, what I'm after is I want to find a sort of an intermediate step. Here's my intermediate step. And that's going to be the following. And bear with me, I don't write very quickly. My goal is to say, find a plane containing one line, but never intersecting the other line. Okay, that's all right. That's my intermediate step. Now, we'll think about why that's helpful as we go along. So, in particular, I'm going to think about this green line. I want to find a plane that has the green line inside of it, but never intersects with the pink line. Okay, well, perhaps before we go too far, can we convince ourselves that this is a useful thing to do? Let's take our picture that we currently have and turn it so that we might have a better angle. So if we turn our picture just slightly, so I'm going to tilt it up fairly dramatically, what happens here is we see that we have this plane with this line in it here, and now above it is this other line going along through. So, oops, sorry, other line that comes along through. Now here's the really cool thing. Because this other line never hits the plane, it turns out that it's always going to be the same distance. You pick any point on this line and you ask how far away is it from the plane. The answer is it's always the same because it's the same amount that we are shifted off. So in other words, if we drop straight down, that distance, if we drop straight down, that distance, so forth and so on, and it's always the same distance from that other line off the plane to the plane. And in particular, it's going to be that distance, whatever it is the distance right there. Now, what's special about that distance? If you look at the angles involved, because I'm going and finding the shortest distance, they're right angles in both places. And right angles means short distance. So this is good news for us. And in particular, this is our great aha insight. Now we say the distance from any point on the line off the plane to the plane is the answer. You might say, wait, what? Well, remember, we said that no matter which point you pick on this pink line, when you drop it down, it's always going to be the same distance, including the distance from our pink line that comes down and hits our green line. So the distance we want is now universally the same no matter which point we pick on the top of one above. So in essence, what we've done is we've saved ourselves a lot of effort. We will never, right now, at least with this process, recover what our points are. That's not what we're doing. What we're doing is we're transforming and saying we can turn our distance problem from line to line to a distance problem point to plane. It's kind of interesting because think about what's going on here. Lines are one-dimensional. So we have a one-dimensional object to a one-dimensional object. So that's somehow two-dimensional. And then we're going from point to plane, which is a zero-dimensional, to a two-dimensional. So again, it kind of works out in a weird way. Okay, so that was sort of the idea. Now, I'm not claiming that this is a totally obvious sort of two-step process, nor am I claiming that this is the only way to do it. This is just the way I like to think about it. And I encourage you to grab some pens and paper and think about what's going on. Start with a couple pens. Okay, add in some paper and start to think about, okay, one of the things you should think about doing, this is an important idea. And this one really is, not just me talking, but it's important to get to the point to say, look, if I just change my perspective, so I pivot so I can look at my situation, that's perfectly allowed. Because in space, it's okay to think about, when I'm thinking about problems in space, and just purely in space, gaining a new perspective doesn't change the problem, but it helps us gain better insight. So it's okay to say, well, I'm not sure what's going on here, but I see things that happen when I look at it in this way. So it's good to be able to sort of have something in your hands, something to work with. Okay, so let's do our intermediate step, and then we'll do our sort of aha step, and then we'll be done with this problem. Of course, there will be more problems. Don't worry. I don't want you to think this is the last problem. There's more problems coming. I promise. I know it. So, how do we go about finding our plane? So let's say, we'll mark these. We'll say this line here is our green line, and this other line here is our pink line. Okay, well, it's not so bad, we say to ourselves. So to find our plane, we say we need a point. Well, we got plenty of points. Pick a point on the line. So we'll just read off the point. We'll have our point is 3, 5, -2. All right, done. What's our normal? Well, now we think about the direction. We have two lines. One line is in the plane, so that definitely has to be something, that direction vector of the line has to be in there. So it has to be perpendicular to -2, 1, 3. And remember that other line, that one floating up here? If you push it down into the plane, it's going to also have the direction in the plane. So if we go to the pink direction, that has to be in the plane. So that is -2, 0, and 4. So there we go. So those are our two things which are perpendicular to each other. So we do our cross product. All right. So I, J, K, -2, 1, 3, -2, 0, 4. And I'm going to try to do this one more or less up here. It's a dangerous thing. You can almost get away with it if you're doing it by cofactor expansion. So suppose I were looking for the I term. I would cross out the row in the column. Then I have a 2 by 2. And I say, what's that determinant? Well, 4 minus 0. So that says the first entry should be a 4. Now for J, I cross out the middle column. And of course, first row, there's a little 2 by 2 matrix. And I say, okay, so it's -2 times 4 is -8. And subtract -2 times 3, which is +6. So it looks like -2. But cofactor expansion, you have that weird flip the sign in the middle, so it should be a +2. So remember that cofactor has that plus minus plus thing going on. And in the last slot, you have that determinant, which is 0, subtract -2, which looks a lot like +2 again. All right, now, because we did this in our head, we're definitely going to check it. Okay, so we have -8 plus 2 plus 6, 0. -8 plus 0 plus 8, 0. We're okay. So this can be used as our normal, or we can scale it. Since everything here is a factor of 2, scale by 1/2 to simplify. And therefore, we can use as our normal 2, 1, 1. Well, now we have our point, we have our normal, we're almost there. So what's our plane? Well, our plane will have the form 2x plus y plus z equals something. Well, now we write down our equation. Underneath, plug in 3, 5, -2. That's 2 times 3 is 6, plus 5 minus 2, and 6 plus 5 minus 2 would get us up to 9. All right, so there we go. That's the answer. Okay, well, not the answer. That's the intermediate step answer. What's the plane that contains the first line but avoids the second line altogether? This plane does it. All right, well, where to next? The answer is we need the distance now. Distance from where to where? Well, pick any point you want. See, that's the beauty of it. You see, before it's like, well, if I have two lines, so I have my two lines here, if I'm thinking about finding the closest point, I have like all these points on the first line I have to choose from, and all the points on the second line I have to choose from, which makes things tough. Now I say, no, forget that, forget it. We only need 1 point. See, this is the great aha. We reduce it, so say, just you have to only pick one point. And that's our great reducing complexity step. So, what's the point? Well, since we can pick any point, we just pick a nice value for t. I say t equals 0 is a great choice. And so, we'll choose the point as 5, 4, -1. So now, I say, I need to know the distance from this point to this plane, and we're done. Well, assuming we remember the distance formula, and, well, there's other ways to do it other than the distance formula, but we do know the distance formula, I hope. If not, we can look it up. It's in our notes. So the distance is the absolute value, ax plus by plus cz minus d. Divide that by the square root a squared plus b squared plus c squared. So it's like we're plugging the point 5, 4, -1 into here. So we do it. 2 times 5 is 10. Plus 4, okay, plus 4, and plus z. So -1, and then subtract 9. -9 over the square root. Now, 2 squared, that's 4. 1 squared, that's 1. And another 1 squared is still 1. Okay, square root 4 plus 1 plus 1. All right, square root of 6. Well, okay, 10 plus 4 minus 1 minus 9. Well, the minus 1 minus 9 cancels with the 10. So what do we end up with? We end up with just 4 on the top and square root of 6 on the bottom. Now, you can multiply by square root of 6 over square root of 6 if you like to do that type of thing. And in that case, you can see that there's an extra factor of 2. So we end up with 2/3 times square root of 6. And we're done. We're done. We found it. We found the distance between the two lines. Okay, kind of an interesting answer. Not so bad. Not so bad. A lot of it, though, this is probably one of the hardest ones geometrically. And at least this approach. There's probably other approaches, but this is how I like to think of it. All right. Well, use your geometry. Use your geometry. All right, on to the next problem. Woohoo! So, given a line and a plane, we say that the projection of the line is what results from taking every point on the line and sending it to the nearest point on the plane. Now, okay, there's this parenthetical comment. This can be thought of as a shadow that the line would cast on the plane if there were a light source placed far away directly above the plane. So let's see if we can sort of get some intuition about what this is saying. So suppose we have our plane. So here's our plane. And we have a line. Okay, so our line is coming through, and in some way, it's not on the plane. It hits the plane and passes through. Now, what we do is for every single point on the line, we just drop down and find the nearest point in the plane. And of course, we do it on the other side as well. And we keep doing that. And what happens is we form a new line, and this new line is going to be in the plane. Essentially, the way we should think of it is that the new line is the closest line that we could find in the plane to the line that we were given. All right, so that's the idea. Now, what is it talking about as a shadow? Well, if you had a light source coming from way up above and shining on, the light would hit the line on top, and the shadow that results is the projection. All right, great, good. So, what's our goal? We're going to actually find one. And you say, okay, find the projection of the line. Here's this line onto a plane. Here's the plane. Well, let's go. Let's think about it. Now, there's a couple of ways to do this. And first off, we know we're going to have to find at least 1 point. So one thing we could do is we could find 2 points. So we know how to find points that are closest. So pick 2 arbitrary points on the line and say, okay, now run the process of finding the nearest point. So we could say, pick this point. There's a point on our line we're looking for. Pick another point. There's another point on the line. Once we have 2 points, we're done. We're not doing it that way because we want to do something different. There's this really cool idea. So we're going to do it a slightly different way. We still have to find a point. Don't get me wrong. We always have to find at least 1 point. But then we're going to use geometry to sort of think about what our sort of missing piece is. So here we go. So let's start by finding our point. So how do we find a point? Well, the point that's easy to spot is that point. You see where that line hits the plane. Well, that point is on the plane. So the nearest point is the point itself. So we say, okay, so to find the point, we can say if we want to find the point, that's the same as finding the intersection. So now, can we find that? And the answer, yes, we can. How do we do it? Well, we have formulas for x, y, and z in terms of t, and we put them in for x, y, and z. So we have 2 times minus 11 over 2 plus 5t plus 4 times minus 11 over 2 plus 3t minus 6 times minus t has to equal 9. Okay, there we go. Well, start multiplying things out. Minus 11 plus 10t. 4 times minus 11 halves is minus 22 plus 12t. And plus 6 times t is 9. Well, 10 plus 12, 22, plus 6 makes 28. So 28 times t equals, now bring the 11 across, gets us to 20. Bring the 22 across, that gets us to 42. So 28t is 42. Now 42, that's the answer to life, the universe, everything. It turns out it's also a multiple of 14, as is 28. So if you divide by 14, you get 2t equals 3, or t equals 3 halves. Now, that is not the point, but it tells us how to find the point. Now we say, look, we know where our time that we have our point of intersection, so we put in 3 halves. So we are going to have our point will be minus 11 halves plus 15 halves, comma, minus 11 halves plus 9 halves, comma, and minus 3 halves. Right? So I'm just putting 3 halves everywhere that there's a t. Well, minus 11 plus 15 makes 4 over 2, gets us to 2. Minus 11 plus 9, minus 2 over 2, minus 1, and then minus 3 over 2. So we now have 1 point. 1 point on the line. We're halfway done. Okay, the last part is to think about the direction. Now, there is kind of a clue here in this problem, and it is this word, projection. And what's the clue? Well, we've seen this word before. We know about the concept of projection. So we can think about, can we use projection in our setting here, and how can we do it? So I'm going to zoom in here, just so I can get a more clear picture. So we have our point of intersection, and then we have our 2 lines. We have the line coming up, and we have the line in the plane. Okay, so, we'll throw some arrows on there, why not? So I want to understand that better. So this line coming up, we know the direction of that line. This line in the plane, we don't know. Okay, so what's the direction of the line coming up? Well, for that, we look at the direction of the line. We can read it off because it's the coefficients for t. 5, 3, minus 1. So I have, this is the vector 5, 3, minus 1. Now, what would we like to do? We'd like to use projection to push it down into the plane. But are we allowed to do that? And why not? The answer is no. The projection formula doesn't work that way. The projection formula says I can project a vector onto a vector. And I can't project a vector onto a plane. That's a different thing. Okay, so what do? Do we give up? And of course we don't. We start thinking, well, is there something that we can project onto which can help us? And now we say, well, it's a plane. And when we're dealing with planes, the vector we should always think about is the normal vector. Okay, so where does the normal vector fit into our picture? Well, the normal vector over here fits in there. Now, it's perpendicular to the line in the plane, but not necessarily to the line that passes through. In fact, it won't be, because if it was perpendicular to the line that passed through, the line that passed through would actually be in the plane. So we have the normal vector that does something like this. Now, what is our normal vector? Our normal vector, we can again read it off. 2, 4, negative 6. That's the normal vector. Well, for convenience, let's scale it so we can use 1, 2, negative 3. So here's the vector 1, 2, negative 3. All right, now, here's the thought. We don't know how to project this vector down into the plane to produce that vector. But we can project 5 through negative 1 onto the normal vector. Let's do that. And then we'll say, does that help us? All right. Well, what can we do? Well, the projection formula, recall the projection of the vector u onto the vector v is the following. It's u dot v over v dot v times v. Now, in our case, what do we want? We want to take the projection of the vector, that's the line, so that's 5, 3, negative 1, onto the normal vector, 1, 2, negative 3. So we take u dot v, 5, 3, negative 1, dot 1, 2, negative 3, divide that by v dot v, 1, 2, negative 3, dot 1, 2, negative 3, times 1, 2, negative 3. Okay, well, barely fit, but we made it in. All right, which is, wow, this is going to be interesting. Okay, 5 plus 6 plus 3. Downstairs, we get 1 plus 4 plus 9 times the vector 1, 2, minus 3. Well, 5 plus 6 plus 3, 14. 1 plus 4 plus 9, 14. So this turns out to be 1, 2, negative 3. In fact, our picture is a little bit off. See, what it says is, by an amazing coincidence, probably they planned it, whoever wrote this problem. They planned it. It turns out that when I project this vector 5, 3, negative 1 onto 1, 2, 3, the 1, 2, negative 3 actually should have stopped there. So that the projection, I'm running out of different colors to use. So the projection here, this part is actually 1, 2, negative 3. Okay. So our vector was too long. Who knew? Well, now we know. So how is that helpful? Here's the great thing. Now what we have is we say, we know how much of 5, 3, negative 1 points in the direction perpendicular to the plane. And in particular, we can come here and say this part right there is 1, 2, negative 3. So this vector that we're looking for satisfies the following. The vector that we're looking for plus the vector 1, 2, negative 3 is equal to the vector 5, 3, negative 1. So we can solve for what we're looking for. That tells us that the vector we want, which is the direction of our line, well, we move the vector across, we subtract. So we get 4, 5 minus 1, 3 minus 2 is 1, minus 1 minus 3 is 2. So 4, 1, 2. That is the direction of that vector. That's the direction of our line. So there's our direction vector of our line. We did it. So we were actually able to use the notion of projection, but because we can't project directly into the plane, we said project onto the normal. Whatever's projected onto the normal, subtract that out from where you started, and that pushes the resulting vector into the plane, which is exactly what we needed. So that is the last piece of our puzzle. We put everything together, we've got all our pieces, and life is great. So our answer, we have x, y, z. So what is that? Well, 2 minus 1 minus 3 halves. 2 minus 1 minus 3 halves. That's our coordinates. And then 4, 1, 2. So plus 4t plus t, that's the 1, plus 2t. And there we go. That is the vector which is inside of the plane and such that it's the closest line to the line that we were given that crosses through the plane. It's projection. So there you go. All right. Wow. That's kind of a fun one. I like this idea of, hey, let's use a projection. And we can use this notion of, well, if I'm looking for something which is, a little bit more complicated, I can project onto a piece and then subtract that piece out and see what's left over. That's a nice idea. It's a really, really lovely idea. Okay, well, on to another problem. Oh, what's next? Find the centers and radii of both, there's going to be 2, spheres which satisfy the following. The sphere is tangent to the plane, 2x plus y minus 2z equals 7, and it's tangent to the plane, 8x minus 4y plus z equals negative 23, and the center of the sphere has to lie on the line x equals 2 plus t, y equals 3 plus 2t, and z equals negative 3t. This is kind of a, what's going on here kind of problem. So let's think of the analogous situation in 2 dimensions. The analogous situation is, instead of thinking of it as being 2 planes, we'd have 2 lines. So we say, well, okay, so we have a line, which again, think of it as our plane, and another line, which again, we think of it as the other plane. So we can think of it as we have plane number 1, and that looks too much like I put a 1 there. So here's plane number 1, And then we have plane number 2. All right. And then what we have is we have some sort of line that's coming through. Well, okay. I'll just put it dotted here. And what are we looking for? Well, the analogous thing to a sphere would be a circle. So we're saying, well, there could be like something here, and looking for a circle, and then maybe here where we could fit another circle in that just barely touches. So that's essentially what we're looking for is these two shapes. Now, our natural response is it possible? Can we do it? Well, I think so. Sure, why not? Now, let's think about sort of some keys here. Now, I think there's a couple of key ideas, but one word kind of gives away what's going to happen. This notion of tangent. So once we understand what the question is asking us, what this tangent means, I think the rest of it will be possible. I mean, it's not going to be easy, but it'll be possible. Well, tangent means we touch. It touches at one point. And in particular, if I'm at a point of tangency, what's going to happen is from my center, the distance to one plane has to match the distance to the other plane has to match the radius. Okay, so here's the idea. What we'll look at is we'll say the distance to, we'll call it plane number 1, that should be, if we just had a single point and I want to say, how big do I put the sphere so it touches just the plane, just barely touches, it's whatever the distance to the plane is, that has to match the distance to plane 2. So that's where we're going to start. We're going to start with this. We're going to say, okay, we're going to set these two formulas for distance equal to each other and figure out when does that work. Now, where do we pick our points? Well, where our points are going to come from the line. So we're going to choose these are the points, and we're going to say for points of this form, 2 plus 3, 3 plus 2t minus 3t, find the distance to the first plane, find the distance to the second plane, set them equal, and figure out what must be true. Actually, that doesn't seem so unreasonable when you start thinking about the process. It's like, okay, they got to touch both planes, we set the distances equal, and see what must be true. It almost seems to flow. Okay, well, now what's the distance? Well, we should remind ourselves the distance formula. Our distance formula is the following. So it is ax plus by plus cz minus d over the square root a squared plus b squared plus c squared. Where, for example, a, b, c are the coefficients, d is the number on the other side, and x, y, z are these pieces there. Well, now a lot of patience, and we just set things up and see what happens. So we begin. So we're going to take the absolute value of 2, so that 2 from there, times the x, which is 2 plus t, plus add y, which is 3 plus 2t, so 3 plus 2t, subtract 2 from that minus 2, times z, minus 3t. Then don't forget you subtract the d, so minus 7. Divide that by the square root of 2 squared plus 1 squared and negative 2 squared. Equals. All right, now the other side. And away we go. Same procedure. Absolute value, 8 times 2 plus t. Okay, so the 8 times x minus 4 times 3 plus 2t. Okay, minus 4 times y plus negative 3t. So that's plus z. And then subtract negative 23. Well, that makes it a plus 23. Divide that by the square root of 8 squared plus negative 4 squared plus 1 squared. All right, good. Well, time for some algebra. Okay, so, we'll make some notes just above here. So let's say we have a 4 plus 2t, then we have plus 3 plus 2t, and here's a plus 6t, and then a minus 7, and then down here, well, this is really the square root 4 plus 1 plus 4, which is square root of 9, which is 3. So, if we clean that up, what do we have? Well, we have 2t plus 2t plus 6t is 10t, and then we have 4 plus 3 minus 7. Oh, wait, that all goes away. Now, here we'll use this to our advantage. You see, so the 4, 3, 7, they all cancel out. Well, let me just mark that so I keep track of what we are doing here. Boom, boom, boom. Ah, it's almost like this was planned. Okay, then there's a 10 times t. 10 can pull out. So we see that the left-hand side simplifies to 10 thirds absolute value of t equals. Now I got to do the other side. All right. Well, similar process. We'll start downstairs. Here we go. We have 64 plus 16 plus 1. Well, that's 81. Square root of 81, that's going to be 9. Wow. Another nice number. Thank you, problem writers. Thank you for caring so much about us. Well, this is good. This is good. We should go buy them a root beer sometime and say, good job. This is a nice problem. Now, let's work on the top. Okay, so 8 times 2, 16 plus 8t. Then we have minus 12 minus 8t, distributing through, minus 3t, and plus 23. So, what's left over? Well, we can see here the 8t subtract 8t. Oh, cancels. Nice. More cancellation. That's cool. That's cool. I like it when things cancel. All right, what else do we have? Well, we have 16 subtract 12 is 4 plus 23 is 27. So that would be a 27 minus 3t and divide by 9. But actually, we can go a little bit further. You see, these terms have a factor of 3. And so we can write this really, and by the way, because of the negative, it doesn't matter whether we have 27 minus 3t or 3t minus 27. When we take the absolute value, same result in the end. So I can rewrite this top as 3 times absolute value of t minus 9. It's the same thing. Now, here's some cool thing. Look at that. The 3 and the 9 and this 3 all combine together to go away. You can imagine, for example, multiplying across by 3 would give you 3 times 3 is 9 over 9. And so, boom, boom, boom. So what are we left with? Well, we're left with the following. We need to have 10 times the absolute value of t has to equal the absolute value of t minus 9. Once we can figure out for what values of t is this true, then we're basically done. It's really going to be slick. Wow, cool. Cool. Okay, so that's our next thing to figure out. All right, well, how do we figure that out? Well, okay. Here's what we can do. Whenever you have absolute value, the idea is get rid of the absolute value. And so we have to think about, well, when do absolute values matter? Let's start with this t. When does absolute value make a difference? Well, there's sort of the before 0 and the after 0. And so the absolute value sort of transitions at 0. How about the t minus 9? Well, there's before 9 and there's after 9. So the absolute value has a transition at 9. So what we need to do is think about the following. Well, we're going to have a couple of possibilities. So we're going to mark 0 and 9. We say, okay, so suppose we're below 0. If we're below 0, in other words, t is negative, then both of these expressions are negative values. So what we end up having is minus 10t, because we need to put a negative here, is equal to 9 minus t, because we got to put a negative. Well, negating is the same as flipping the order. And now we say, okay, well, we can arrange. We can do a little bit of move this there, move that there. And if we do that, we get negative 9 is equal to 9t, or t equals negative 1. All right, so at t equals negative 1, this equation is true. And you can see that, right? 10 times 1 is the absolute value of negative 10. Good. Now, that's one case. How about from 0 to 9? Well, because I'm above 0, I can drop the absolute value, but here I still need to change the sign because I'm below 9. So this becomes what? Well, now in the second part, we get that 10t is equal to 9 minus t. Now here, divide, we get 11t has to equal 9, or t equals 9/11. Okay, so that's the second possibility for t. Now, I should step back a second. I kind of shortchanged us a bit. I just said t equals negative 1, and I was very nonchalant. I was like, okay, great, that's an answer. Let's be careful here. Does t equal negative 1 actually work? The answer is yes, because it's below 0. Does t equal 9/11 actually work? Well, yes, because it's between 0 and 9. Well, let's do our last case. So this last case is over here, and we come all the way down because we're running out of space. And now, if I'm above 9, the absolute values mean nothing. So we get 10 times t equals t minus 9, and we do the same thing as before, and we get, okay, 9t equals negative 9, or t equals negative 1. Now you might say, hey, we already found that. But the more correct answer is to say, this is something we can't use. Because I can only get this formula when I was saying, if I'm assuming I'm above 9. So I can't say, well, if I'm above 9, I should be negative 1. Well, negative 1 is not above 9. So that's why we throw that out. It just turns out to match up in that case. But be careful, sometimes it doesn't. All right, well, we're basically done because we found the t that works. Now, how do we put everything together? So we need to find the center and the radius and write down our answer. So center, radius. Let's do the center. So to do the center, we plug in. So plug in negative 1. 2 plus negative 1. 1. 3 plus 2 times negative 1. 1. Negative 3 times negative 1. 3. Okay, 1, 1, 3. Great. Perfect. Nice answer. The radius. Well, where is that? It's actually right here. that's our radius. Because remember, this expression simplified to 10 over 3 times the absolute value of t. This was our distance, which is the radius of the sphere. So we know that we're dealing with t equals -1, so our radius would be 10/3. Okay, so there's our first sphere. Sphere number 2. This one will be a little bit more interesting because we get 9/11. Well, 2 plus 9/11. That's be 22/11 plus 9/11, which is 31/11. Okay, that's our 2 plus 9/11. Then our next term here, 3 plus 2 times 9/11. So that would be 33/11, so that's our 3, plus 18/11. Well, 33 plus 18 is 51. So, comma, 51/11. And comma, -3 times 9/11 is -27/11. Okay, so that's our center. What's our radius? Well, multiply 9/11, an absolute value, which is 9/11, times 10/3. Well, the 9 and the 3 can do a little bit of cancellation, and so we end up with our radius would be 10 times 3/11, which is 30/11. And now, there we go. There's our center and our radii of our two spheres. Wow, that's cool. It's amazing we can find it. It's such a fun problem. And of course, we could find it in general, but in this case, it was really carefully crafted so that we could get a reasonable answer. And I know you're looking at this and saying, that's reasonable? Yes, it is. You could have had a lot worse. So yeah, that's a very reasonable answer. But good, great. Okay, well, time for another problem. Ooh, looks like a word problem. Okay, there's a two-stage rocket which will move through three-dimensional space. Initially, the rocket is located at position -3, -4, 1. Now, in the first stage, for every unit of fuel used, we'll move the rocket in some direction. So, of course, we represent that by a vector. So, the amount of fuel we use tells us how much we move in that direction. So, we can move just a little bit or a lot. It just depends. How much fuel do you have? In the second stage, for every unit of fuel used, you move the rocket in a different direction. So we start someplace, and then we move by some amount in some direction, and that's stage 1. Stage 2, head off in another direction. And that's it. Of course, now we start thinking, okay, what are we trying to do? All right, given that the goal is to get the rocket as close as possible to a small moon located at the position 4,411/2. Determine how much fuel should be used in each stage. Now, notice it doesn't say get the rocket to 4,411/2. Well, maybe we can't actually reach it. Now, why not? Well, let's think about what's true. You see, I can start and I can move in one direction and move in a different direction. That's only 2 directions. In space, there should be 3 directions. So if I'm only allowed that 2 degrees of motion, back and forth this way, back and forth this other way, then what can I reach? It's a plane. And that's only a small part of space. So it's very unlikely that our target, which is some point out in space, just happens to coincidentally lie on the plane. So, okay. So what's going on? Well, let's try to get sort of an intuition about what's happening in this problem. So, what do we have? Well, we're starting somewhere at -3, -4, 1. So there's our initial location, where we're if we use the terminology of rockets. That's where we're blasting off from. Now, what happens? Well, what happens is that after we blast off in stage 1, we can move a little bit in a certain direction. So essentially in stage 1, we're moving back and forth in a fixed direction. Once we're finished with that stage, we're going to move in some other direction. And that moves in some other way. And now if we think about, well, what is it we can actually reach? Well, if we combine these two types of motion, we see, lo and behold, what we can actually get to is a plane. So we say, perfect. By doing these two stages, we can get our rocket to anywhere we want in the plane. But where do we want to get to? Well, remember, we have a goal. We want to get close to a moon. So we say, all right, here we'll mark, let's say here's our moon. And I know what you're thinking, that's no moon. Well, okay, all right. It's a representation of a moon. But all right, what do we do with it? Well, what we do is we say, okay, we want to be close to the moon. So we imagine that we say, well, what are we after? Well, we're going to go straight down, and there's some point here in the plane, which is as close as possible to the moon. See, we want to be as close as possible. That's our goal. We see it right there. So, in some sense, what do? Well, we have a couple of pieces we have to put together to solve this puzzle. We have to say, okay, let's figure out where we're shooting for. All right. If we want to figure out where we're shooting for, we have to figure out, okay, what can we actually get to? And so let's start there. So we're going to figure out what can we reach, and then the next step, among all the things that we can reach, which one is the closest to our goal? And then the next step is, okay, now that we know which point we're trying to get to, how do we get there? So there's going to be more or less 3 big steps to this problem. So let's start with the first step. What can be reached? So there we go. Step 1. What can we reach? Now, we actually have already seen there's the intuitive answer. It's a plane. So the real question is, what's the plane? So for us to figure out what the plane is, whenever we're talking about a plane, we need 2 pieces of information. We need a point, and we need the normal. Well, a point, that's a freebie. We know where we're starting. That point, -3, -4, 1. So, -3, -4, 1. The normal. Well, when we think about finding a normal, one of our best strategies is to ask, do we know 2 directions in our plane? Because if we do, our normal has to be perpendicular to both. Well, we do know some directions in the plane. And in particular, we know the directions that the rocket moves in stage 1, and the rocket moves in stage 2. Those are directions in our plane, and therefore we say, aha, the normal has to do what? It has to be perpendicular to 2, 3, 5, and it also has to be perpendicular to 1, 1, 2. All right, well, now I have 2 vectors our normal has to be perpendicular to, and therefore the cross product. All right, so we pull out our cross product tool. So we have what? Well, I, J, K, 2, 3, 5, 1, 1, 2. All right, so we're going to try to do this compactly. So we'll do it by cofactor. Remember how cofactor works? You cross out the first row and the first column. And you say, okay, take that little determinant. It'll be 6 minus 5. 1. Now it goes in the second entry. Now, similar thing, cross out the first row, but now the middle column, take that determinant, it would be 4 minus 5. 4 minus 5, -1. But because of cofactor, you got to remember to change the sign in the middle. It's kind of that weird thing. That's the part that almost always, if anyone does cofactor expansion and they get it wrong, it's because they lose the sign for that part. Okay, last part. We cover the first row, last column. Again, take the determinant. 2, subtract 3, -1. Well, that's actually pretty nice. Okay, so let's check. Dot product, right? 2 plus 3 minus 5, 0. 1 plus 1 minus 2, 0. So we have the right normal vector. 1, 1, -1. Okay, so now we have our point, we have our normal, we can make a line. Sorry, we can make a plane. Okay, so what's our plane going to be? Our plane becomes x plus y minus z, coefficients 1, 1, -1 from there, equals, now plug in, -3, -4, subtract 1. -3 minus 4 subtract 1 is -8. All right, so we now know what can be reached. Any point that satisfies x plus y minus z equals -8. Fantastic! Woohoo! Progress! Progress, and progress is good. It makes us feel like we're getting closer to the answer because we're getting closer to the answer. Now we enter into stage 2. And of course, that's a dangerous thing to use in this problem because there's stage 1 and stage 2. But maybe we'll say part 2 of the problem. We know what can be reached, and now we ask, well, among everything that can be reached, what's the ideal thing? So in terms of the picture, we're looking for that point right there. Well, that's the same as saying, I have a point, what's the nearest point in the plane? We've solved this problem before. At least if you've been working through all the problems, right? Well, this time it's a little bit tough. I'll agree. If you work through all the problems this time, you're in great shape. Here's a reminder what we do. We say, hey, this line, segment, it's really part of a line. So we can imagine just extending it up and down. Say, all right, so why? Well, we know this is a point. In fact, what is it? It's the point 4, 11/2. So we know this point. And now, what do we want? Well, we want that point. So if we have a point on the line, and we can use the normal vector as the direction of the line, well, that gives us the line. And then we can say, let's figure out what this point is over there. Okay, so here we go to our next part. Number 2. So we want the nearest point to 4, 11/2, which is on the plane. So we're going to make this line. So we say, okay, what do we need? Well, we're going to say our line has a point 4, 11/2, and our direction, well, it's going to be the perpendicular direction to the plane, which means it's a normal vector, which means it's 1, 1, -1, because we've worked out what the normal vector is. So the line that we're after has the following form. X equals y equals z equals 4, 11/2 plus t minus t. Now, that's the line coming from the moon down to the plane that we're after in a perpendicular way. We need that point. That's the place where the line we just found intersects our plane. Okay, well, how do we find where lines and planes intersect? Well, we take our x, y, z, and we put them in for our x, y, z. So we'll now do that computation. So what will that give us? Well, it gives us the following. X, which is 4 plus t, plus y, which is 4 plus t, minus z, 11 halves minus t, equals negative 8. X plus y minus z equals negative 8. So let's clean it up. A t plus a t plus a t, because right, the minus goes through, would give us 3t. Well, equals minus 8, then minus 4 plus 11 over 2. I'm just bringing the 4, and the 11 over 2 across. Okay, so let's be careful here. If we group these together, that's minus 16. Minus 16 is minus 32 over 2. Minus 32 over 2 plus 11 over 2 is negative 21 over 2. So 3 times t is negative 21 over 2, which tells us t equals negative 7 over 2. Divide by 3. Okay, now, is that a point? No, of course not, because it's a value for t. But we can now take our value for t and plug it in, and we get our point. So, we're ready to say, what is the point we're shooting for? Well, so we need to get to, we're going to take 4, subtract 7 over 2. Well, that's 8 over 2, subtract 7 over 2, says we need to get to x equals a half. And we then say, what about y? Well, same thing. 4 subtract 7 over 2, so y equals a half. And how about z? Well, 11 over 2 minus 7 over 2 makes 18 over 2, also known as 9. So that's our target. So written as a point, 1/2, 1/2, 9. So coming here, this point right here, 1/2, 1/2, 9. We want to start from here, and we can now see what's happening. Stage 1, we move along. Stage 2, we move here. We drop off whatever we need to, because that's our goal. And then, well, who knows? We just need to get to that point. Now, we've figured out where we need to get to. The last thing is, how do we actually get there? So this is the part which the problem really asked us at the beginning. How much do we need to spend in our fuel? So we have 2 phases. We have, stage 1, stage 2. How much fuel goes into each stage to get us to where we need to be at in the end. Okay, so let's think about that. Well, so part 3. So what do we call part 3? Well, we'll say it's determine the fuel for each stage. And what do we have? Well, we say let's start at our point, and I'll write everything as a vector just to make things easier to follow. -3, -4, 1. Then A will be how much fuel we use in stage 1. So however much fuel we use times the vector 2, 3, 5. This will be, when we combine that together, where we're at the end of stage 1. Then we go into stage 2, so we times that 1, 1, 2. So B, that's how much fuel we're going to use in stage 2. So this, all 3 combined, so initial point, change in stage 1, change in stage 2. That's where we're going to be at the end of stage 2. We know where we're going to be. We've got to end up at our target. So that's got to equal 1/2, 1/2, 9. So we say, good, here we go. We've got to figure out what's the right combination of A and B that makes this all work. Well, let's dig into it. So what we're going to do is we're going to take this and just write it entry-wise. So say, what's in the first slot? What's in the second slot? What's in the third slot? And if we do that, we'll get an idea of the formulas that have to be satisfied. So, for instance, -3 plus 2a plus b has to equal a half. Okay, minus 4 plus 3a plus b has to equal a half. And 1 plus 5a plus 2b has to equal 9. So those are our equations. So we need to solve those for a and b. Now, you might think, is it possible? Can it be solved for a and b? And I hope so. Well, let's clean it up a little bit. So this becomes 2a plus b. If you add 3, a half plus 3 makes 7 halves. Then you get 3a plus b. If you add 4, a half plus 4 makes 9 halves. And if you do the last one, you get 5a plus 2b equals 8. Now, at this stage, you could be a little bit nervous because you could say, hold on. We have 3 equations, but we only have 2 unknowns. In other words, we're trying to have 3 things be satisfied all at once, but we only have 2 things that we can choose. And when that happens, you should be nervous, and rightfully so. You might call, there's a technical term you might hear from time to time called this is overdetermined. We've thrown in too many constraints. But take a closer look. Notice something. If you add the first 2 equations together, 2a plus 3a gives you 5a. b plus b gives you 2b. 7 halves plus 9 halves is 16 halves, also known as 8. So it turns out the first 2 equations combine to give the third equation. So there's really, it says, look, the third equation doesn't give us anything new. So we really have 2 equations and 2 unknowns. Aha! That makes us feel better. So now let's try to solve those. So what do we have? We have 2a plus b equals 7 halves. So that's our first equation. And 3a plus b equals 9 halves. So we look at this and say, how can we combine things together to cancel stuff? Well, I see the b's are just perfectly set up for canceling. So let's just do the following. We're going to, let's multiply the first equation by -1, and then we'll add. Why? Well, you'll get minus 2a plus 3a is a. Minus b plus b, 0. Minus 7 halves plus 9 halves, 2 halves, or 1. So a is 1. Once you know a, you can get b for free. Just plug it in. So you get 2 plus b equals 7 halves. So I'm just plugging in a equals 1 into the first equation. Subtract 2 from both sides, and you get b equals 3 halves. And now we're actually done. Because A, that's how much fuel you should use in stage 1, and B is how much fuel you should use in stage 2. So we'll just, only thing left to do is write down our answer. All right, so stage 1, 1 unit of fuel. Stage 2, 3 halves units of fuel. And that is how we should use our different stages combined together to get from our initial point to the point which is closest to our moon. In retrospect, it all seems easy. Wow, beautiful. It's a fun problem. There's a lot of little pieces going on here, and it's easy to make mistakes. I've made mistakes doing this problem before, I'll be honest with you, which is why I try to go slow. This is the right answer, though. So I know because I've done this enough times before that it does work out. I think what makes this challenging is you have to think about, how do I get there? Because you say, I have a big goal, but I can't quite reach it. And so how do I get from my current state to the big goal? Well, the answer is don't try to do everything at once. Break things down as a process and say, okay, well, what can I reach? No, that's a good question. If you're saying, I want to reach something, what can I reach? And if you're saying, well, I have this goal, well, what's my real goal? I mean, maybe it says, I want to get as close as I can. Okay, how do I figure that out? And all right, so it's just be careful, combine ideas, be patient, ask yourself questions. What's something I can do? What's information I haven't used yet? And be patient. That's an important thing. There's a great piece of advice I learned when I was an undergraduate for solving problems. And it's a very simple process. You try something, and if it doesn't work, try something else. But never give up. Okay, good. And that brings us to our last problem. There's an end? Yes, there definitely is an end. It's not that we've done every single problem imaginable, but I think we've done enough that by now, hopefully we've got some good geometric intuition going here. Okay, so this is our cool down. Well, do we really ever have a cool down? Find the plane which contains the points 3, 1, 2 and 4, 0, 1, and which is farthest from the point 2, negative 2, 3. Interesting. Now it's very easy to construct a plane which contains the points 3, 1, 2, 4, 0, negative 1, and is closest to the point 2, negative 2, 3. Super, super easy. Just take the plane that contains those 3 points, and life is good. But now we have to think about, well, farthest from? How do we do that? What's our intuition? And what's the process for figuring that out? Okay, so we begin. So let's think about what's true. Well, certainly we know one thing for sure. We know it has the points 3, 1, 2 and 4, 0, 1. So we have these 2 points out here, 3, 1, 2 and 4, 0. Whoops, I said 1. It's negative 1. So here we have these 2 points. And once you have 2 points, you also have to have the line connecting the 2 points. So what does that say? Well, if we think of sort of our intuition, we can kind of say the following. I have a line on the plane, and then, then I have the plane. So if I think of a piece of paper as being the plane and this line, what happens is I can sort of rotate or pivot, if you will, about that line. And I get all these different planes. So I have all this variety of planes going through here. All right. So there's a lot of planes. Now, how do we understand our problem to make it easier for ourselves? Well, let's do the following. We're going to change perspective. And this is a really useful idea, and one that we're going to really buy into when we get up to integration. Our ability to change the way we look at something is going to be very helpful for figuring out what's going on. So how do we change our perspective? Well, what we'll do is instead of having this line here to pivot around, we're just going to change it so that we look straight down that line. So we're going to look straight down. So instead of seeing a line, it now looks like a single point. So lo and behold, we've stacked these 2 points right on top of each other. Now, what's happening? Well, this line is now a single point. In the meantime, there is some other point. Okay, so that's the point. I'll put it here, 2, negative 2, 3. So this dot represents the line. And now let's think about the planes. Remember how we said we could pivot? So we have this pivoting ability. So as we look at down the line, what we have various pieces that we could look at. All right. So those are the examples of planes we can see. And now the question becomes, what's the right plane? All right. Well, we have to think of the geometry. So here we have sort of a fun idea. Look at it this way. I claim that the right plane is right here. And it has the following property. Namely, if you were to take the point which you want to be farthest away from, and you were to drop down straight to the line, that should form a right angle. Now, I'm not dropping down to the points, I'm dropping down onto the line. So, why is that? Well, suppose it didn't. Okay, if it didn't form a right angle, what would happen? Well, let's just sort of draw the scenario and reason through it. So, where's my colors? Oh, there you are. So I have my dot, I have the point, I have the line, and I say I'm not forming a right angle. So what happens is the following. I say, okay, what's the nearest point? Well, the nearest point I drop into would be over here. And I say, well, compare it to the line, dropping to the line. I see, dropping to the line is further than dropping to the nearest point. So that says that in the scenario where I've not tilted the plane so that the nearest point is on the line, my closest point, my distance, I should say, from my point to my plane has decreased. Okay, so, good. This is the key idea. Now, it doesn't feel like we've made a lot of progress, but we're making tremendous progress. We're actually just a couple of steps away from being done. Now, where do we go next? Well, let's start talking about some direction vectors. We can talk about the direction vector that goes between these 2 points. And that's going to be important, so let's go ahead and mark it. So 3 goes to 4, 1 goes to 0, -1, 2 went to -1, means -3. So 1, -1, -3. All right, now what? Well, we want to find a vector, which, a second vector, right? So our normal vector, we know it has to be perpendicular to this direction, 1, -1, -3. Because 1, -1, -3 is a direction of a line in the plane. Now, how do we get the second one? Well, we say, look at our picture. What we'll do is we know that we have this notion. The plane we want somehow has to be perpendicular to this direction. Well, so what we can do is we can say, well, let's make this plane here. So this is the plane through the 3 given points. And I'm talking about 3, 1, 2, 4, 0, -1, and 2, -2, 3. That's going to be perpendicular to the plane we want. So how do we find that normal vector? Because if we can find that normal vector, it's going to be perpendicular to the normal vector that we want. All right, well, to find that normal vector, we'd find 2 vectors in that plane. All right, well, we know a vector in that plane. It's 1, -1, -3. A second vector in that plane is just pick a point, let's say 3, 1, 2, and go to the point 2, -2, 3. So 3 to 2, down by 1. Then we go 1 to -2, down by -3. 2 to 3 is by 1. All right, so down by 1, down by 3, up by 1. So now we say perfect. These two vectors are in the plane that runs through the 3 original points. So let's take the cross product and see what we get. So if we take the cross product, we get the following. So we have I, j, k, 1, minus 1, minus 3, minus 1, minus 3, 1. So that would be minus I plus 3j minus 3k. Going the other direction, plus k, but need to subtract it. Plus 9i, but need to subtract it. Plus j, but need to subtract it. So we get minus 10, 2, minus 4. Well, check our work. We have minus 10, minus 2, so that's up to minus 12, plus 12. Good. Here we have plus 10, minus 6, minus 4, 0. Good. That works. So this is going to be a normal vector for this plane up and down here. Well, we can pick any vector we want that's a scalar multiple of that. Well, let's scale by a half just to simplify. And so we end up with minus 5, 1, minus 2. So what's next? Well, the vector that we found is a normal vector to a plane which is perpendicular to the plane that we want, which means, lo and behold, that this vector is also perpendicular to the normal vector that we're after. And now we say, aha, now we have two vectors which are perpendicular to the normal vector that we want. Perfect, perfect. And so what do? We take their cross product. Now, at this point, you're probably thinking, we already took a cross product to find a normal. Yeah, and that was a stepping stone to be able to take another cross product. So this is a double cross product, twice the amount of fun. Cool. Okay, so here we go. Round 2. I, j, k. 1, minus 1, minus 3, minus 5, 1, minus 2. So 2i. Then it's going to be 15j. And then it'll be plus k. And then the other direction, 5k, but remember you have to subtract. And then it'll be minus 3i. We have to subtract, so it really becomes a plus 3i. And then it's a minus 2j, but you have to subtract. It really becomes a plus 2j. So that looks like 5, 17, negative 4. Check our work, right? So 5 minus 17 would be minus 12 plus 12. 0. Good. Minus 25 plus 17, that's minus 8, plus 8 more. 0. Now, this is the normal vector to the plane we're looking for. And now, we're in great shape. Because this says these are our coefficients. And we have some points, so it's just a matter of putting it all together. So our answer is 5x plus 17y minus 4z equals something. And the only thing left to do is, what's the something? Well, just pick a point. I'll pick the one with the 0 because I like using things with lots of zeros. So 5 times 4, 20. 17 times 0, 0. Minus 4 times minus 1 is plus 4. So we end up with 5x plus 17y minus 4z equals 24. And we're done. Now, this is a problem where we probably would not have guessed this just by random trial and error. You have to think of the geometry, what's going on here. And it sort of helps to think about, well, let's look down this line. In essence, one of the things that happens is when you look down the line, what you're doing is you're reducing the dimension. You're saying, hey, let's take one dimension out of play so that this one-dimensional object, which is a line, becomes a zero-dimensional object, which is a point. And I say, okay, now I see when I'm thinking about things in 2D, it's like, okay, if I want to be as far away from a point as possible and I'm a line, then I should somehow be perpendicular when I think about dropping down to it. And that's what we were trying to get to, is that this needs to be perpendicular when we drop down. So, okay, well, we can find the perpendicular part. That seems easier because we have information about these pieces. Now we have two things which are perpendicular, and that helps us find that. And we succeed. And it's kind of, you don't expect to have to do two cross products because you're like, wait, if I do two cross products, aren't I undoing it? Well, no, it's a little bit more subtle than that. And we get an answer. What an answer. Well, if you started at the beginning and you just kept going all the way through, you may have fallen asleep. I know I probably would. It's been a couple of hours here, and it's really been a couple of hours. Some really fun problems, some really challenging problems mixed in here and there. Thank you for being so patient and hanging in there. I hope this is helping you. And if nothing else, I like the idea that someone will see this part. Who knows? I hope so. I really hope that you're doing well. Take care of yourself. Be good to yourself. And have fun with math. We'll see you again. Bye.